Welcome to Night Cosmos Sleep, where we explore the deepest mysteries of the universe through a slow and peaceful rhythm of storytelling. If a spacecraft could travel close to the speed of light, it would do more than shorten the journey to the stars. Time aboard the ship would separate from time on Earth. The light ahead would shift in color, interstellar dust would become a serious threat, and the return journey could bring the travelers home to a world that had already passed through many generations. But before imagining a spacecraft carrying human beings, we must begin with a simpler question. How close can matter actually come to the speed of light? The answer can be found inside an enormous tunnel beneath the ground, where protons are accelerated until they move so fast that they almost seem to catch up with light. Yet no matter how much more energy they receive, they can never reach that limit. Inside a tunnel buried deep beneath the ground, humans have accelerated particles of matter to such extraordinary speeds that they can complete more than 10,000 laps around a vast circular track in a single second. These particles travel so close to the speed of light that the difference nearly disappears when only the first few digits are considered. Yet no matter how much additional energy the system supplies, none of them can reach that limit. The remaining gap is incredibly small, but within that tiny distance lies the greatest obstacle facing every dream of sending a spacecraft to the stars. This tunnel belongs to the Large Hadron Collider, commonly known as the LHC, located at CERN beneath the border region between Switzerland and France. The accelerator ring has a circumference of nearly 27 kilometers and lies deep underground, containing two parallel vacuum pipes. Inside them, beams of protons travel through an environment from which almost all air has been removed. Powerful superconducting magnets guide the particles continuously around the ring, preventing them from striking the walls of the pipes. The protons are not sent directly into the main ring and instantly accelerated to extreme speeds. They must first pass through several smaller accelerators, gaining energy in stages before entering the LHC. Each time the proton beams pass through accelerating cavities, they receive another boost of energy, while magnets positioned along the tunnel continuously adjust their paths and keep them moving around the curve. By the end of this process, the protons can reach more than 99.999999% of the speed of light and circle the tunnel over 10,000 times every second. At lower velocities, adding energy causes the speed of an object to increase quite noticeably. But once a proton is already moving extremely close to the speed of light, that familiar relationship begins to change. CERN continues supplying energy to the particle beams. Their momentum continues to rise, and the energy released in their collisions becomes greater, yet their speed increases by only an extremely small amount. The protons can move even closer to the limit, adding more nines after the decimal point, but they can never reach the exact speed of light. The closer they come to that boundary, the more energy each additional increase in speed requires. When a proton is moving slowly, a given amount of energy can change its velocity significantly, but when it is already traveling near light speed, the same amount of energy produces only a tiny change. Most of the added energy increases the particle's momentum and total energy, making its collisions more powerful rather than increasing its speed in the familiar proportion. This is one of the clearest practical demonstrations that the speed of light is not merely a number written in an equation. Humanity has built an enormous machine, accelerated matter to nearly that limit, and then continued feeding energy into it. The same result has been observed again and again across generations of particle accelerators. Matter can approach the speed of light to an almost unimaginable degree, but no object with mass has ever been observed crossing that boundary. The primary purpose of the LHC is not to study how to build an interstellar spacecraft. Physicists use it to explore the deeper structure of matter, investigate fundamental particles, and recreate on an extremely small scale some of the conditions that existed in the early universe. Yet the protons racing through its tunnel unintentionally provide a very practical starting point for thinking about near-light speed travel. They show that matter can truly be accelerated to extraordinary velocities, while also revealing how difficult the final portion of that journey becomes. A proton is an unimaginably small object. It does not need to carry air, water, food, or any life support system. It requires no protective shell against radiation, no temperature control equipment, and no engine of its own traveling alongside it. The entire acceleration system remains fixed around the tunnel, while the proton is simply pushed through an environment prepared in advance. Every component added to a spacecraft increases its mass, and the engine must accelerate all of it. It must push not only the passenger compartment, but also tanks of water, air supplies, machinery, shielding, and fuel that has not yet been used. When the spacecraft carries additional fuel to reach a higher speed, that fuel makes the vehicle heavier, requiring the engine to use even more energy to accelerate it. Adding still more fuel demands larger tanks and stronger supporting structures, making the problem increasingly complex. For the protons at CERN, the electrical power, magnets, and cooling equipment all remain outside the particles themselves. An interstellar spacecraft could not rely on a tunnel millions of kilometers long already built between two stars. Unless it used energy transmitted from a distant source, it would have to carry its engine and most of the energy required for the journey. Everything used to produce thrust would therefore become additional mass that must also be accelerated. The difference between a proton and a spacecraft is not limited to size. A proton does not need to survive in the way humans understand survival. If a proton beam is lost from the pipe, the system can be stopped and restarted with another beam. A crewed spacecraft would need to keep its entire structure operating reliably for years or decades, because a serious failure in interstellar space could not be repaired by sending a technical team from Earth. At no point would the spacecraft see an invisible wall ahead. The speed of light would not appear as a glowing boundary in space, nor would the ship collide with anything as it approached. The engines would continue running, fuel would continue being consumed, and the instruments would continue recording an increase in speed, but that increase would become smaller and smaller compared with the energy being spent. The spacecraft could continue moving ever closer to the limit, but the final step would never come. Light differs from a spacecraft in one fundamental way. A photon traveling through a vacuum does not begin at rest and gradually accelerate. From the moment it is emitted, it moves at the speed of light. A spacecraft, by contrast, is an object with mass. It begins its journey at a much lower velocity and must continually receive energy in order to accelerate. Bringing an object with mass all the way to the exact speed of light would require an amount of energy with no finite limit, something no engine, power plant, or civilization could ever provide. The practical question, then, is not whether a spacecraft can travel at exactly the speed of light. According to our current understanding of physics, that is impossible for any object with mass. The more meaningful question is how close a spacecraft could come, because even traveling at only a fraction of light speed would carry it far beyond anything humanity has ever built. If a spacecraft reached 10% of the speed of light, it would be vastly faster than anything humanity has built today. Even so, the journey to Proxima Centauri would still take more than 40 years if we counted only the period of steady flight and left acceleration and deceleration out of the calculation. At 20% of light speed, the travel time could be reduced, but the demands on energy, materials, and shielding would become far more severe. Once the spacecraft approached 50% or 90% of the speed of light, the challenge would no longer be simply a matter of building a more powerful engine. The sparse gas particles and tiny grains of dust scattered through space would strike the hull with far greater energy. Light from ahead would begin to shift in frequency. Radiation would become a more serious danger, and time aboard the ship would gradually separate from time on Earth. Every increase in speed would not only raise the energy requirement, but also introduce new problems that never existed during slower journeys. An ultralight probe could accept many risks that a crewed spacecraft could not. It would not need to maintain breathable air, a comfortable temperature, or artificial gravity for passengers. It might consist only of a thin sail, a few small sensors, a computer, and a communication system. The lower the mass, the less energy required for acceleration, which is why interstellar concepts closest to present-day technology focus mainly on extremely small probes rather than ships with living quarters. A crewed spacecraft would need many more layers of protection, but every layer would make it heavier. As the mass increased, so would the required energy, while the engines and fuel tanks would have to grow larger to meet that demand. This creates a cycle that makes the gap between accelerating a proton and accelerating a human spacecraft far greater than the difference in size alone. The problem becomes even harder because the ship would not only need to reach a high speed. As it approached the destination star system, it would have to slow down if the passengers hoped to enter orbit, observe planets, or search for a place to land. All the energy used for acceleration would somehow have to be dealt with. If the spacecraft carried its own fuel for braking, that fuel would also need to be accelerated from the moment the ship left Earth, increasing the initial mass even further. A vehicle unable to slow down could do little more than pass through the star system. After decades of travel, it might fly near a planet for only a few hours before continuing onward and disappearing into space. That could be acceptable for a small probe designed only to take images and transmit data, but it would be nearly meaningless for a group of people who had left Earth in search of a new world. CERN does not provide a solution to these problems, because the LHC only needs to accelerate extremely small particles inside a tunnel built in advance. Yet the protons there still teach us something important. Matter is not stopped at some arbitrarily low speed. It can move extraordinarily close to the speed of light, so close that the remaining difference appears only in tiny digits far beyond the decimal point. Even then, nature preserves a gap that can never be completely erased. Perhaps one day humanity will build a probe capable of reaching a significant fraction of light speed. Farther in the future, a crewed spacecraft might leave the solar system fast enough for relativistic effects to become unmistakable. At that point, the journey would be determined not only by the distance between the stars, but also by the mass of every instrument, every layer of shielding, every tank of water, and every system needed to keep human beings alive. Every kilogram accelerated to an extreme velocity must be paid for with energy. While the spacecraft is still moving slowly, that cost may rise in a relatively familiar way. But the closer it comes to the speed of light, the more energy each small additional increase requires. The distance to Proxima Centauri remains a challenge. Yet the first obstacle is not the 4 light-years separating the two star systems. It is the energy required to accelerate an object trillions of times more massive than a proton. The engines could continue running, and the fuel could continue being consumed, but with every passing minute, the same amount of energy would increase the ship's speed by a smaller amount than before. No component would necessarily need to fail, and no accident would have to occur for the journey to encounter its limit. The barrier is created by the relationship between energy, matter, and velocity itself. Before humanity can bring a spacecraft close to the speed of light, it must first find an energy source that our present civilization does not yet possess. The engine continues to run, fuel continues to be consumed, and the spacecraft continues to accelerate. Yet with every passing minute, the same amount of energy increases its speed by a smaller amount than before. No component has failed, the fuel has not lost its power, and the space ahead is not creating some invisible resistance. This change occurs simply because the spacecraft is moving ever closer to the speed of light, where the familiar relationship between energy and velocity no longer resembles what humans experience in everyday life. When a car accelerates along a road, much of the engine's energy must overcome friction, air resistance, and mechanical losses. In interplanetary space, those forms of resistance are greatly reduced, allowing a spacecraft to continue drifting after its engine shuts down without constantly burning fuel to maintain its speed. But maintaining speed and continuing to accelerate are two different problems. To make the spacecraft move faster, the engine must still supply energy, and the closer it approaches the speed of light, the greater the energy required for each small additional increase in velocity. The difficulty does not come only from the cabin where the passengers live. When the engine produces thrust, it must accelerate everything being carried, from the outer hull, cooling systems, guidance computers, water tanks, air supplies, and medical equipment to the fuel that has not yet been used. A large portion of the engine's energy is not spent moving people toward the destination star, but pushing the very fuel that will continue to be burned months or years later. If engineers add more fuel so the spacecraft can accelerate for longer, its initial mass increases. Greater mass requires more thrust and energy, forcing the ship to carry even more fuel. Additional tanks need a structure strong enough to support them, and that structure makes the spacecraft heavier still. A larger engine also requires a larger cooling system, stronger pressure lines, and more material to protect against vibration, heat, and radiation. Every solution added to extend the spacecraft's range creates more mass that the engine must carry throughout the journey. This is the cycle that makes chemical rockets, despite being highly effective at carrying humans away from Earth's surface, unsuitable for near-light speed travel. Chemical fuel releases energy by rearranging the bonds between atoms, producing hot gases that are expelled backward to push the rocket forward. This method is powerful enough to overcome Earth's gravity and place a spacecraft into orbit, but the amount of energy available from each kilogram of fuel is still far too small compared with the demands of relativistic flight. One of the most seriously studied ideas is to use light to push an extremely lightweight sail. Light has no rest mass, but it carries momentum. When a photon strikes a surface and is absorbed or reflected, it transfers a very small force to that surface. This pressure is almost insignificant for a large object, but if the sail is light enough, wide enough, and continuously illuminated by a powerful beam, that tiny force can accumulate over time and produce a significant velocity. Solar sails have already been tested in space, but natural sunlight weakens as a spacecraft travels farther from the sun. More ambitious proposals for interstellar acceleration use a vast laser array positioned near Earth or in orbit. The system would focus energy onto the sail, pushing it forward without requiring the spacecraft to carry all the fuel needed for acceleration. The vehicle itself would carry only the sail, scientific instruments, communication equipment, and a small power source for operation after it left the laser beam. NASA Innovative Advanced Concepts has funded studies of directed energy propulsion, including proposals for laser arrays capable of accelerating thin, lightweight probes to relativistic speeds. These studies do not describe ships carrying hundreds of people. Instead, they focus on extremely light devices, perhaps as small as a microchip or weighing only a few grams. Another NASA study examined a beamed energy architecture that might accelerate probes to nearly 10% of the speed of light, but this remains a technological proposal with many unresolved milestones, not a system ready to be built. The difference in mass determines nearly the entire problem. A sail and several sensors weighing only a few grams might be accelerated by an extremely powerful laser beam within a relatively short time. A crewed spacecraft would have to be millions or billions of times heavier because it would need living quarters, radiation shielding, air recycling equipment, water, food, course correction engines, and many backup systems. If the same acceleration were maintained, the energy transmitted to the spacecraft would have to increase with its mass, while the sail itself would need to become larger and withstand more intense light without melting or deforming. A laser beam traveling across a great distance cannot remain perfectly narrow forever. The light gradually spreads, reducing the amount of energy that actually reaches the sail as the spacecraft moves farther away. Keeping the beam sufficiently focused would require an enormous transmitter, optical elements working together with extraordinary precision, and a sail that remained correctly aligned while its velocity continued to rise. Even a slight error could shift the thrust away from the center, causing the sail to rotate, tear, or drift out of the beam. The sail material would need to be almost weightless, yet still reflect most of the incoming light to avoid absorbing too much heat. It would have to withstand immense power in a vacuum, where there is no air to provide cooling. Even if only a small fraction of the laser's energy were absorbed, the temperature could rise enough to destroy the material. Research into laser sails is therefore not only about building a powerful source of light, it is also about developing materials, controlling the beam, stabilizing the vehicle's orientation, and maintaining communication with an extremely small device across distances of many light years. Another approach would use a particle beam instead of a beam of light. Particles accelerated from a distant station could transfer momentum to the spacecraft or to a specially designed sail. In some configurations, matter particles can carry more momentum than photons for the same amount of energy, but they are also more difficult to keep concentrated across enormous distances. Charged particles repel one another, respond to magnetic fields in space, and may spread apart before reaching their target. Some proposals combine lasers with particles or tiny pellets of matter, creating a high-speed stream that pushes the spacecraft from behind. NASA has funded studies of architectures such as Proxima, which combines laser and particle beams, as well as concepts using streams of accelerated microscopic particles to propel a vehicle. These studies show that transmitting energy from a distance is not limited to science fiction, but most still focus on probes or rapid missions within the solar system, not crewed spacecraft traveling close to the speed of light. For an ultralight probe, this level of risk may be acceptable. Hundreds or thousands of small devices could be launched, with only a fraction needing to succeed. A crewed spacecraft could not rely on those odds. It would need to handle failures on its own, correct its course, sustain human life, and eventually slow down upon reaching the destination star system. If all its thrust came from a laser station in the solar system, braking after traveling several light-years would become a problem with no simple solution. Nuclear energy sources can provide a higher energy density than chemical fuel. Fission reactors have been used to generate electricity in many applications on Earth, while radioisotope power sources have allowed space probes to operate where sunlight is too weak. But producing electricity over long periods is different from generating enough thrust to accelerate a massive spacecraft to relativistic speeds. The reactor, radiation shielding, heat conversion systems, and radiators would all add to the vehicle's mass. Even if fusion reactions could be controlled, the energy they produced would not automatically become useful motion. Much of it might emerge as heat or as neutrons that are difficult to control, requiring heavy shielding and large radiators. The spacecraft would once again have to carry additional material to manage the very energy source expected to reduce its mass. A vast distance still separates a laboratory reaction that produces energy from an engine capable of operating continuously for decades in space. Antimatter is often regarded as one of the highest density energy sources allowed by known physics. When matter and antimatter meet, their mass can be transformed into energetic particles and radiation. In theory, a very small amount of fuel could release far more energy than a chemical reaction or nuclear fission. This is why antimatter often appears in more ambitious models of interstellar propulsion. But antimatter is not a ready-made fuel source waiting to be extracted. It must first be created using energy, then separated from ordinary matter and confined by electromagnetic fields to prevent it from touching the walls of its container. Current production efficiency is extremely low. The amount of antimatter humanity has created is tiny, and storing enough of it to power an engine remains far beyond present technological capabilities. NASA studies of antimatter propulsion emphasize these very obstacles, from production, storage, and transportation to the challenge of converting annihilation energy into controlled thrust. The obstacle to near light speed travel, then, is not simply finding a more powerful fuel. Humanity would need to solve the problems of energy supply, conversion, efficiency, engine mass, heat-resistant materials, thermal management, radiation shielding, system durability, and deceleration at the same time. A technology may appear highly promising in one area while making the problem more difficult in another. Laser sails would allow a spacecraft to travel without carrying its own fuel, but they would require an enormous energy-transmitting array. Fusion could provide a higher energy density, but it would demand reactors and shielding systems that do not yet exist. Antimatter offers extraordinary energy potential, but producing and storing it on the required scale is nearly impossible with current technology. At present, humanity possesses no energy source, material, or propulsion system capable of accelerating a large spacecraft to relativistic speeds. Today's fastest vehicles remain far below the velocities at which time dilation would become an obvious part of the journey. Yet this does not mean research has stopped. Programs exploring light sails, beamed propulsion, particle streams, and ultralight probes are gradually testing individual pieces of the problem. The most practical designs do not begin with a city traveling between the stars. They begin with thin sails, sensor-equipped chips, experimental lasers, and materials capable of reflecting intense light without being destroyed. One NASA proposal for gram-scale probes traveling toward Proxima Centauri assumes the need for a laser system with a power of roughly 100 gigawatts, together with an enormous optical receiving facility on Earth. Even for a vehicle weighing only a few grams, the required infrastructure would be immense, revealing how much farther technology must advance before a crewed spacecraft could even be considered. The path from a device weighing a few grams to a ship carrying human beings is extraordinarily long, but it is not completely empty. Every light sail experiment tests a new kind of material. Every study of beamed energy reveals the precision needed to track a vehicle across great distances. Every nuclear or antimatter engine design clarifies the challenges of heat, radiation, and fuel storage. These ideas have not yet carried humanity to the stars, but they help distinguish what is merely attractive on paper from what can gradually be tested. The energy source required to carry a crewed spacecraft close to the speed of light does not yet exist as a system humanity can build and operate. No power plant on Earth can provide the complete combination of energy, beam-focusing capability, heat-resistant materials, and reliability needed for such a journey. Still, the first pieces of the problem have begun to appear in laboratories, research programs, and missions using light sails on a vastly smaller scale. However a future engine may operate, it will still obey the same fundamental limits. The heavier the spacecraft, the more energy it will require to accelerate. The closer it comes to the speed of light, the more expensive each additional increase in velocity becomes. And if human beings are aboard, the engine cannot release all its power in a single moment simply because the energy is available. Machines can be reinforced to withstand violent acceleration, and a small probe can be launched with forces strong enough to destroy a living body. But the people inside a spacecraft would still have bones, blood vessels, soft organs, and hearts that must continue pumping throughout the journey. So, even if a future civilization discovers the necessary energy source, the spacecraft could not reach an extreme velocity within only a few seconds. The next challenge would no longer be the power of the engine, but the amount of force a living body could endure as the entire world around it began to accelerate. The spacecraft is moving faster than any large object humanity has ever built, yet inside the cabin, a drop of water drifts slowly through the air as though nothing unusual were happening. The travelers hear no wind rushing beyond the hull, feel no vibration beneath the floor caused by speed, and are not pressed backwards simply because the ship is moving so quickly. Outside, the planets have fallen far behind, and the sun has become only one bright point among countless stars. But within the cabin, breathing, the movement of a hand, and the quiet sounds of machinery continue as calmly as they did during the first days after leaving Earth. On the ground, people usually sense speed through clues in their surroundings. When a car moves quickly, air flows along its body. The wheels carry vibrations from the road. The scenery outside the windows recedes, and every turn pulls the body to one side. On an airplane, the sound of the engines, vibrations through the fuselage, and changes in pressure also remind passengers that they are moving. Yet most of these sensations do not come directly from velocity. They arise because the environment is acting on the vehicle, or because the vehicle is changing direction or speed. A spacecraft could travel at thousands of kilometers per second without its passengers feeling as though they were racing through space. If every window were covered and no instrument displayed information from outside, they would have almost no way to use their bodies to distinguish whether the ship was stationary, drifting slowly, or moving at a significant fraction of the speed of light. A cup on the table would not slide backward simply because the velocity had become enormous. The air inside the cabin would not gather at one end, and the passengers' heart rates would not change merely because the numbers on the navigation screens had grown very large. What the body feels is not velocity, but a change in velocity. When the engines begin producing thrust, the entire spacecraft accelerates forward, while the passengers' bodies tend to preserve their previous state of motion for a brief moment. The seats, floor, and safety restraints transfer force from the ship to the body, creating the sensation of being pressed in the direction opposite the acceleration. If the engine's thrust rises suddenly, that sensation becomes stronger. If the force increases gradually and then remains steady, the body may adapt to an almost constant sense of weight. Humans have experienced this during every spacecraft launch. Astronauts are not pressed into their seats because the rocket is moving fast, but because its velocity is increasing rapidly. Once the main engines shut down and the spacecraft enters orbit, the vehicle is still traveling at tens of thousands of kilometers per hour, yet the feeling of heaviness disappears almost immediately. The astronauts leave their seats, objects begin to float, and their bodies enter a state of near weightlessness, even while the spacecraft continues racing around Earth at tremendous speed. An interstellar spacecraft would follow the same principle. While the engines were operating, the passengers would feel the thrust. When the engines shut down and the ship continued coasting at a constant velocity, that sensation would disappear. Without another system to create gravity, everything inside the cabin would begin to float. A spoon lifted from the table might drift in front of the person using it. A drop of water escaping from a cup would contract into a small sphere, and the passenger hair would no longer fall across their shoulders. The spacecraft's speed might then be greater than that of any vehicle ever built, but inside, the condition of weightlessness would be no different in principle from what astronauts have experienced aboard the International Space Station. The ship would not need to burn fuel continuously to maintain its velocity. With no significant resistance, it could continue traveling for a very long time without slowing down as a car would on a road. The engines would need to operate only when the spacecraft wanted to accelerate further, change direction, or prepare to decelerate. If the goal were to carry humans to another star system in less time, shutting down the engines too early would make the journey much longer. One approach often considered in models of interstellar travel is to maintain moderate acceleration over an extended period. Instead of producing an extremely powerful burst of thrust for only a few minutes, the engines would operate continuously for months or years, increasing the spacecraft's velocity little by little while the passengers remained under conditions their bodies could endure. For someone living inside the cabin, the difference between gravity and steady acceleration might be difficult to detect within a small enclosed space. An object released from the hand would still fall toward the floor. A person lying down would still feel their back pressed against the mattress, and water would remain at the bottom of a cup. If the spacecraft were large enough and its propulsion system operated smoothly, everyday life could continue much as it does on Earth, even though the entire living compartment was being pushed through space at a velocity increasing every second. The acceleration would not need to be extreme to create a clear sensation. If maintained near the level of gravity to which the human body is accustomed, passengers could walk, eat, and work without spending years floating through the cabin. This would provide more than comfort. Long periods in microgravity can weaken muscles, reduce bone density, and alter the circulatory system because the body no longer has to work against a constant downward pull. Continuous thrust could reduce some of these problems by giving the body a stable downward direction. However, this gravity-like sensation would exist only while the engines continued changing the spacecraft's velocity. If the propulsion system failed or was shut down to conserve energy, the passengers would no longer remain standing on the floor. A blanket resting on a bed might slowly lift away, small unsecured objects would drift from the table, and water inside the pipes might require pumps to keep flowing in the proper direction. The living quarters would have to be designed for both conditions, because a journey lasting many years could hardly rely on the assumption that the engines would never stop. Even if the thrust remained steady, the passengers might still notice very subtle changes. The human body is sensitive to engine vibrations, the sound of pumps, and oscillations traveling through the spacecraft's frame. A propulsion system powerful enough to accelerate a large vehicle for an extended period would generate heat and mechanical forces that would need to be controlled carefully. If the thrust were not perfectly uniform, those inside might feel their weight change slightly with each cycle of engine operation. During a real journey, the spacecraft could not continue accelerating forever in the same direction. To stop at Proxima Centauri or another star system, it would need to begin slowing down long before reaching its destination. There would be no friction brakes in interstellar space, and no runway long enough to absorb its motion. The most direct method would be to rotate the spacecraft until its engines faced forward, then continue producing thrust in the direction opposite its movement. The moment the spacecraft turned around would be one of the most complicated stages for the passengers. If the main engines shut down before the rotation began, the artificial sense of gravity inside the cabin would disappear, and everything would return to weightlessness. Small maneuvering thrusters, or a system for rotating the ship, would gradually change the orientation of the entire structure. The stars on the observation screens would move sideways, while the direction once called forward slowly exchanged places with the rear. This could create an experience that would be difficult to understand through bodily sensation alone. Before the spacecraft turned, the passengers stood on the floor because the engines were pushing the vehicle faster toward the destination star. After the turn, they would still stand on the same floor because the engines were slowing the ship down. The force acting on their bodies might feel almost identical, even though its meaning for the journey had completely changed. Only the navigation instruments and images from outside would reveal whether the spacecraft was in the first or second half of its voyage. The ability to maintain steady acceleration over such a long period, however, would depend on the available energy, the durability of the engines, and the spacecraft's ability to release heat. A system operating for years would have to endure millions of cycles without accumulating serious damage. Moving components, control valves, magnets, and heat-resistant materials would all need to be monitored, because even a small change in thrust could affect both the structure of the spacecraft and the health of its passengers. The human body can withstand high acceleration for short periods, especially when positioned correctly and supported by specialized equipment. But a strong force sustained over time would place continuous pressure on the heart, blood vessels, and internal organs. Blood could be driven toward one part of the body, depriving the brain of oxygen or placing excessive stress on surrounding tissues. An uncrewed probe could therefore endure a violent acceleration that a spacecraft carrying humans would have to avoid. A small probe has no bones, lungs, or circulatory system. If its structure is strong enough, it can withstand acceleration forces far greater than a human body can tolerate and reach high speeds in a much shorter time. Its electronics can be secured firmly to the frame, while sensitive components can be embedded in protective material. In a living body, every cell is affected by acceleration, and soft organs may shift slightly in relation to the skeleton when that acceleration changes suddenly. For this reason, even if an extraordinarily powerful energy source were discovered, a crewed spacecraft could not simply switch its engines to maximum power and reach near-light speed within a few seconds. Such acceleration could destroy the vehicle or make survival impossible for the passengers. The energy would have to be released in a controlled way, slowly enough for the body to adapt, yet sustained long enough for the spacecraft to reach the required velocity before the journey became too long. If the thrust were maintained at a level close to Earth's gravity, the spacecraft's velocity could increase significantly over many months. The passengers would not feel as though they were undergoing one continuous launch, because the weight pressing on their bodies might feel much like standing on the ground. They would recognize that the ship was changing velocity only through the displays, the shifting positions of celestial objects, and the increasingly faint signals arriving from home. Inside the sleeping quarters, blankets would remain over the passengers' bodies. In the dining area, food would stay on plates, and water could still be poured into cups. Plants in the biological compartment would continue directing their stems and roots according to the acceleration, even though no planetary soil lay beneath them. These ordinary routines could continue while, outside, the spacecraft had already surpassed speeds once considered unreachable for a large vehicle. On an ordinary day, the ship might produce only the steady, low vibration of its engines. The passengers would wake according to cycles of artificial light, inspect the systems, exercise, tend the plants, and exchange messages that had taken months or years to cross the distance. The velocity outside would not make their subjective experience of time run faster or slower. An hour on a clock inside the cabin would still contain 60 minutes, and every minute would still contain 60 seconds. A forgotten meal would still grow cold. Hair and fingernails would continue to grow. A wound would still need time to heal. Children aboard the ship would still grow older, and adults would continue aging at a pace that felt entirely normal to them. There would be no moment when the passengers felt their thoughts slowing down or their hearts beating according to a different kind of time. Every process in the body, from chemical reactions inside cells to the activity of the brain, would remain synchronized with the clock beside them. At first, the difference might be so small that no one would notice it in everyday life. Messages from home would still carry familiar faces, cities would retain their old appearance, and the voices of family members would seem almost unchanged. But as the spacecraft's speed increased and the journey continued, the gap between the two streams of time would begin to widen. Those aboard would not feel it within their bodies, because everything inside the cabin would continue operating as before. It is this normality that would make the journey so difficult to comprehend. No warning would sound when the spacecraft's time began to separate from Earth's. No boundary would be crossed, and there would be no sensation of the body leaving the present behind. The passengers would continue walking on a floor created by the thrust of the engines, listening to air move through the ventilation ducts, and watching their faces age slowly in the mirror. Meanwhile, the clocks left behind on Earth would continue running according to their own rhythm. Each time the spacecraft accelerated, changed direction, or moved closer to the speed of light, the relationship between the two systems of time would become more complex. The travelers would not be frozen, nor would they escape aging, but they could experience less time than those who never left home. Everything inside the cabin would still feel normal. Meals would cool, hair would grow, and hearts would beat with their familiar rhythm. Yet the watch on a traveler's wrist would no longer remain synchronized with the clocks left behind on Earth, and what was once only a prediction of physics was measured with real clocks by human beings many decades ago. In 1971, two scientists, Joseph Haefele and Richard Keating, carried atomic clocks aboard commercial flights and sent them around the world. One group of clocks traveled eastward, while another traveled westward, and additional clocks remained at the United States Naval Observatory as a reference. When they were all brought back together, they no longer displayed exactly the same time. The difference was far smaller than the blink of an eye, but it was large enough for precise instruments to detect, and it agreed with the predictions of relativity. From the outside, the journey looked nothing like an experiment probing the nature of time. The clocks sat in airplane seats, passed through airports, and experienced takeoffs, landings, and changes in time zones like ordinary pieces of passenger luggage. They were not taken near a black hole, did not travel at a significant fraction of the speed of light, and never left Earth. Simply by moving around a familiar planet at the altitude of a commercial airplane, they accumulated a different amount of time from the clocks that remained on the ground. An ordinary clock may run fast or slow because of its springs, temperature, battery, or internal mechanical parts. The atomic clocks used in the Haefele-Keating experiment were different because they kept time using the extremely stable energy transitions of cesium atoms. They still had uncertainties, but they were stable enough to detect differences, lasting only a few billionths of a second. Time dilation was no longer an idea confined to equations. It had become a measurable quantity that could be carried onto an airplane, flown around the world, and examined again when the journey ended. Two effects appeared during the flights. Because Earth is rotating, an airplane traveling eastward moves faster in the direction of the planet's rotation when measured against a reference frame that does not rotate with the ground, while a westward flight has a different relative motion. Motion causes clocks to accumulate time at a different rate, while flying above the surface places the aircraft in a slightly weaker gravitational field, producing an effect in the opposite direction. The final result depends on the aircraft's speed, altitude, direction of travel, and the amount of time the clock spends in the air. The difference was measured only in nanoseconds, far too small for any passenger to notice. A person could still eat, sleep, talk, and walk through the airport without feeling that the journey had taken away or added a fragment of time. The human body has no sense delicate enough to detect such a tiny shift, but atomic clocks do. Before the flights, the clocks kept the same rhythm. When they returned, they carried the traces of different journeys through space-time. GPS satellites orbit more than 20,000 kilometers above Earth and carry highly stable atomic clocks. Each satellite continuously broadcasts information about its position and the exact time its signal was transmitted. A phone or navigation device receives signals from several satellites and calculates its position by measuring how long the radio waves took to travel from orbit to the ground. Because those signals move at the speed of light, even a tiny error in time can become a significant error in distance. The clocks aboard the satellites do not accumulate time at the same rate as clocks on the ground. Because the satellites move quickly, special relativity causes their clocks to run about 7 microseconds slower each day than clocks on Earth. But they are also farther from Earth, where gravity is slightly weaker. so general relativity causes their clocks to run about 45 microseconds faster each day. When the two effects are combined, satellite clocks would run about 38 microseconds faster per day than clocks on the ground if the system were not corrected. 38 microseconds is still an extremely short interval. In everyday life, no one would care if a wristwatch gained less than a thousandth of a second over several days, but GPS does not use time only to tell the hour. It converts time into distance through the speed of the radio signal, so the error would accumulate and quickly cause the calculated position to drift away from the user's actual location. Relativity is not a decorative addition that makes the system slightly more precise. It is one of the conditions required for the entire navigation network to function correctly. Engineers do not wait for satellites to reach orbit and then express surprise when their clocks begin to drift. The clock frequencies are prepared in advance, and the control system is designed to account for relativistic effects. Ground stations continue monitoring each satellite's orbit, time, and condition, while correction data is transmitted upward to preserve the necessary synchronization. Every time a vehicle follows a route, a ship determines its position at sea, or a telecommunications network uses GPS timing. Predictions about motion, gravity, and the passage of time quietly contribute to the result. A person may never have read any of Einstein's equations and still use relativity whenever they open a map on their phone. The small dot on the screen exists because of many layers of technology, including satellites, atomic clocks, radio signals, and corrections invisible to the human eye. If time truly passed at the same rate at every altitude and every velocity, some of those corrections would not be necessary. But the satellites continuously show otherwise. The difference in GPS remains small because the satellites still move very slowly compared with light. They travel around Earth far faster than most vehicles on the ground, but their speed is still only a tiny fraction of the cosmic limit. As a result, motion-based time dilation appears only at the level of microseconds per day. For a spacecraft accelerating between the stars, however, the separation between two streams of time could grow from millionths of a second into days, years, or even decades. The difference would become visible only when the clock aboard the spacecraft was compared with a clock on Earth. If the ship were not moving extremely fast, the gap between them might remain very small. But as its velocity approached the speed of light, every year experienced by the travelers could correspond to many more years at home. Both sides would feel that their own time was passing normally, yet when they exchanged data or met again, they would no longer have aged as expected before departure. The first signals from Earth might reveal nothing alarming. The screen would still show familiar rooms, faces the travelers had seen before leaving, and voices whose tones had barely changed. Family members might talk about the weather, a new job, small changes in the neighborhood, or a child who had just started school. For those aboard the ship, each message would be a fragment of ordinary life sent across the darkness. But communication between the stars could never take place like a live phone call. Radio signals and light must obey their own speed limit. Once the spacecraft was 1 light-year from Earth, a message sent from home would need at least a year to reach the place where the spacecraft had been when the signal began its journey, while the ship itself continued moving. Any reply from the travelers would also require a long time to return. Every face appearing on the screen would therefore belong to the past. The travelers would not see their families as they existed at the moment the message was received, but as they had been when the signal left Earth. A smile might have begun its journey across space months or years earlier. By the time it reached the spacecraft, the person who sent it would already have lived through another part of life that the receiver could not yet know. A year aboard the spacecraft might pass through steady routines, maintenance cycles, familiar meals, and long hours spent observing the sky. By the time the next message arrives, loved ones on Earth may have aged by more than a year. At first, the changes may appear only as a few strands of gray hair, deeper lines around the eyes, or a child who has grown noticeably taller. The travelers still remember the day of departure with perfect clarity, but back home, that day is receding more quickly into history. There is no single moment announcing that an entire generation has passed. The change arrives through one message at a time, each lasting only a few minutes but separated by periods of silence that grow increasingly long. A familiar person disappears from the screen and begins to be mentioned in the past tense. a new voice takes their place and sends greetings instead. That person may know a great deal about the traveler through photographs, recordings, and family stories, but to the person aboard the ship, they are still a stranger. The spacecraft would not need to travel at exactly the speed of light to create this separation. It would only need to move fast enough and maintain that velocity for long enough for the accumulated difference between the two sides to become significant. An effect that produced only a few nanoseconds aboard an airplane and a few microseconds per day on a satellite could become a visible part of a human lifetime. If the travelers journeyed to a nearby star and then returned, they might experience only a fraction of the time that had passed on Earth. The exact difference would depend on the spacecraft's speed, the duration of acceleration and deceleration, and the full path of the journey. There is no single ratio that applies to every flight. The principle, however, remains unchanged. The closer the spacecraft moves to the speed of light, the less time its clock accumulates compared with clocks that remain behind. This is not a way for humans to stop aging. The travelers would still have to live through every day, and they could still die if the journey lasted longer than their natural lifespans. Time dilation would only allow them to reach Earth's future more quickly, according to their own passage of time. They would not see the future instantly, nor could they travel back into the past. The spacecraft would simply follow a path that made the interval between departure and return longer for those at home than for those aboard. From the traveler's point of view, during a period of steady motion, they could also describe the clocks on Earth as running at a different rate. The clear asymmetry appears only when the entire journey is considered, because the spacecraft must accelerate, turn around, and decelerate in order to return and reunite with Earth. Those who remain behind continue along a nearly steady path, while the travelers change their state of motion to leave and then come back. When the two sides meet again, their clocks can be placed beside one another, and the difference no longer depends on how long any signal took to travel. An interstellar journey is not required to confirm that clocks following different paths can accumulate different amounts of time. Haffele and Keating carried clocks aboard ordinary airplanes and measured exactly that. GPS satellites must continue accounting for the same effect every day they operate. Modern optical clocks have even measured gravitational differences between two positions separated by only a very small change in height, revealing that time is far more sensitive to its environment than human senses can detect. The evidence already exists in laboratories, aboard airplanes, in orbit, and within devices used every day. Time does not wait for a near light speed spacecraft before beginning to change. It is already changing around us, but on scales too small for the body to notice. An interstellar spacecraft would only magnify the effect until the difference was no longer measured in billionths of a second, but seen in the faces of those who remained behind. Only the messages would gradually reveal what had happened. Parents' hair would turn silver, children would become adults, and people who had not yet existed when the spacecraft departed would begin addressing the traveler by a name preserved in family history. Each new face would become emotional evidence of the same truth atomic clocks measured in 1971. Two people can separate, live completely normal lives, and still accumulate different amounts of time. The travelers would not feel that they had stepped outside the flow of the universe. They would simply be following a different path through space-time, while the clock beside them recorded the length of that path. When the spacecraft returned, the time that had passed aboard and the time that had passed on Earth would both be real. Neither clock would be broken, and neither side would have experienced an artificial form of time. They would simply have recorded two different journeys. When the travelers used their instruments to measure the remaining distance to the star ahead, the result would also differ from the number calculated before departure. From Earth, Proxima Centauri would still lie more than 4 light-years away. But aboard a spacecraft moving close to the universe's speed limit, the distance along the direction of travel could be shorter. Not because the star had changed its position, but because space and time cannot be separated into two completely independent parts. The clock has shown that the traveler's journey can be shorter in time. The next measurement will reveal that the distance ahead can also be shorter from their point of view, and the nearest star will no longer seem as far away as it did while the spacecraft was still resting on the launch pad. Proxima Centauri lies about 4.24 light-years from Earth. Even a radio signal leaving Earth at this moment and traveling through a vacuum at the speed of light would need more than 4 years to reach the region of space around that star. No rocket can shorten the signal's travel time, because radio waves are simply another form of light. Yet for a spacecraft carrying humans and moving fast enough, the journey could be far shorter in terms of the time experienced by the passengers themselves. The ship would not outrun light, and Proxima Centauri would not actually move closer to Earth. What changes is the way those aboard the spacecraft and those who remain behind measure the distance and time between the two places. Proxima Centauri is the closest known star to the Sunday. It is a small red dwarf, far dimmer than the Sun, and belongs to the Alpha Centauri system alongside the two brighter stars Alpha Centauri A and Alpha Centauri B. From Earth, the two main stars can appear as a prominent point of light in the southern sky, while Proxima is too faint to be seen with the naked eye. Even though it is the Sun's nearest neighbor on an astronomical scale, it is still so distant that its light must cross more than 4 years of empty space before reaching an observer's eyes. Because light takes time to travel, the Proxima Centauri seen through telescopes today is not the star as it exists at this exact moment. Every photon gathered by the telescope's mirror left the star more than 4 years ago. If a major event occurred there today, Earth would not learn about it until years later. Whenever humans look into the sky, they are looking into the past. Whether the delay is only a few minutes for the Sun or millions of years for distant galaxies. Before the spacecraft leaves Earth, engineers can determine the distance to Proxima Centauri through astronomical measurements. They track the star's position as Earth travels around the Sun, compare its tiny shift against the background of more distant stars, and use that change to calculate its distance. The value of approximately 4.24 light-years is entered into the navigation system and becomes the initial length of the journey. If the spacecraft travels much slower than light, that distance remains almost unchanged in ordinary calculations. A vehicle moving at 1/10 the speed of light would still need more than 40 years to cross it, even before acceleration and deceleration are included. The answer lies in the fact that distance is no longer measured in the same way within two systems moving relative to one another. From Earth, Proxima Centauri remains more than 4 light-years away. Those who stay behind can track the spacecraft, determine its velocity, and calculate that the journey must still take more than 4 years if the vehicle approaches but never reaches the speed of light. Nothing in Earth's measurement becomes shorter. Light remains the fastest thing that can travel between the two locations, and the spacecraft always arrives after a signal transmitted at the same moment. The instruments aboard the spacecraft also operate correctly, but their result is not the same as the one measured from Earth. In the reference frame moving with the vehicle during a period of steady flight, the distance between the point of departure and the destination star has contracted along the direction of motion. The travelers do not believe they are crossing more than 4 light-years in an impossibly short time. From their perspective, the distance they must travel is no longer the full 4.24 light-years measured before the spacecraft accelerated. While the ship is still on the launch pad, the passengers and the people on the ground agree on the distance to Proxima Centauri. Their rulers, clocks, and maps belong to nearly the same state of motion. As the spacecraft accelerates, it gradually enters a different frame of motion. Once its velocity becomes extremely high and the engines temporarily hold it in a nearly steady phase of flight, the passengers no longer divide space-time into distance and time in the same way as observers on Earth. Those aboard do not see the universe suddenly shrink in one obvious moment. There is no sound when the distance ahead becomes shorter, and no boundary appears on the navigation display. The change accumulates throughout the acceleration. As the instruments continually update the spacecraft's state of motion, they also update the way positions and times of outside objects are measured. In the spacecraft's frame, the remaining distance to the destination star gradually contracts. Even though Proxima Centauri remains at its familiar distance in Earth's frame, this does not mean the star is being pulled toward the bow of the spacecraft by some mysterious force. Proxima Centauri does not leave the Alpha Centauri system and rush forward to meet the passengers. What changes is the structure of the measurement itself. Distance is not a single absolute number on which every observer in the universe must agree. To determine the length between two widely separated places, an observer must define the positions of both at the same moment. But the meaning of the same moment is not identical for observers moving very rapidly relative to one another. On Earth, scientists determine the positions of the departure point and Proxima Centauri using a network of synchronized clocks. Aboard the spacecraft, the passengers use a different system of clocks, one suited to the motion of the vehicle. The two groups do not choose the same set of events as occurring simultaneously. Because of that difference, they do not measure the same distance between the two ends of the journey. No object needs to be physically crushed or distorted for this to happen. Inside the spacecraft, the corridor remains exactly as long as the engineers designed it. The bed still fits the person lying on it. The tables and chairs do not become thinner. The doors still close within their frames, and the distance from the front of the ship to the rear remains unchanged in the passengers' measurements. If someone raises an arm in front of them, it keeps its familiar length. Their body is not flattened along the direction of travel, and they do not feel the atoms within them being compressed. The change becomes apparent when the travelers measure the distance to objects that are not moving with the spacecraft. In their frame, Earth is receding behind them, while Proxima Centauri approaches from ahead. The distance between the two star systems along the direction of motion is shorter than the value measured in a frame nearly at rest with both systems. The passengers can therefore travel from one to the other in less personal time than light needs to cross the 4.24 light-years measured from Earth, without ever exceeding the speed of light in any local measurement. If the spacecraft traveled at 90% of the speed of light, and the periods of acceleration and deceleration were temporarily ignored, people on Earth would see the journey take nearly 5 years. For the passengers, the elapsed time might be only about 2 years. The spacecraft would not be moving faster than light. In the traveler's frame, the distance to Proxima Centauri would have contracted enough for the ship to remain below light speed, while the journey lasted only that amount of personal time. If the velocity increased further, the difference would become even stronger. At nearly 99% of the speed of light, Earth would still have to wait more than 4 years for the spacecraft to reach the region around Proxima Centauri, but only a fraction of a year might pass aboard the ship if acceleration and braking were ignored. The travelers would not feel that they had crossed a distance beyond the reach of light. In their measurements, the path ahead would have contracted dramatically along the direction of motion. Those figures describe only a simplified case in which the spacecraft has already reached a high velocity and maintains it steadily. A real journey would need time to accelerate after leaving Earth, turn around, and then decelerate before reaching the destination star system. During those stages, the spacecraft's frame of reference would be changing continuously, making the distance impossible to describe with one fixed value. Even so, the overall meaning remains the same. The travelers could experience far less time than the original distance might suggest, as long as the ship reached a velocity sufficiently close to the speed of light. One commonly used model for a crewed voyage has the spacecraft accelerate at roughly the strength of Earth's gravity during the first half of the journey, then turn around and decelerate at a similar rate during the second half. The passengers could remain standing on the floor for most of the trip while the ship gradually gained speed and then slowed before arrival. For a nearby star such as Proxima Centauri, the maximum velocity might not reach the most extreme fractions of light speed if the acceleration period were not long enough. But time dilation and length contraction would still begin to appear. In theory, a traveler could cross vast regions of the Milky Way in far less personal time than the length of the journey measured from Earth would suggest. This would not make the galaxy a small place for those who remain behind. The Milky Way would still be about 100,000 light-years across, and light would still need roughly 100,000 years to travel from one side to the other in the galaxy's frame of reference. If a spacecraft traveled near light speed, Earth would also have to wait almost that long for the vehicle to complete the crossing. Those aboard might experience only a small fraction of that time because the distance along the direction of motion would be contracted in their frame. But by the time the journey ended, the outside world would have continued for thousands or tens of thousands of years. The ability to travel far within a human lifetime would not preserve the era left behind. A spacecraft might carry its passengers across an immense distance without making them age by a corresponding amount, but it could not stop time from passing for the stars, planets, and civilizations behind them. With Proxima Centauri, the separation would not need to extend across thousands of years. It is still the nearest star system, so even a round trip at very high speed would create a much smaller difference in elapsed time than a journey across the galaxy. Yet the principle would already be fully present. The travelers and the people on Earth could begin on the same day, compare their clocks, and agree on the distance. Once the spacecraft accelerated, they would no longer share the same way of measuring space and time. From Earth, observatories would continue tracking the spacecraft's signal. They would calculate its position from the time the signal took to return, correct for the vehicle's motion, and compare the result with the predicted position of Proxima Centauri. On their map, the ship would still cross each portion of the distance of more than 4 light-years and would never move faster than a radio signal traveling alongside it. Aboard the ship, the passengers would follow a different map built from measurements within their own moving frame. Earth would recede behind them. Proxima Centauri would approach from ahead, and the remaining distance would decrease more rapidly than the original number suggested. They would not need to assume that Earth's instruments were wrong. Both maps would describe the same journey correctly from 2 different states of motion. The travelers would not need to understand every equation in order to live with this change. The navigation system would calculate the remaining travel time, the position of the destination star, and the moment when the spacecraft needed to turn around and begin slowing down. The clocks inside the cabin would continue running normally, while the sensors constantly gathered light from ahead. Each day, Proxima Centauri would appear slightly brighter on the displays, not because the star had suddenly changed, but because the actual distance between the ship and the star was decreasing. The light reaching the spacecraft would still carry information from the star's past. While the ship remained near Earth, the photons arriving from Proxima Centauri would have left more than 4 years earlier. As the spacecraft raced toward the star, it would meet waves of light traveling in the opposite direction. Photons emitted at progressively later moments would reach the ship one after another, allowing the passengers to observe a history of their destination that came increasingly closer to its present. If a signal were sent from Earth at the same moment the spacecraft departed, that signal would always reach Proxima Centauri before the vehicle. The travelers might experience less than 4 years during their journey, but this would not reverse the order of arrival. In their frame, the distance would be shorter, and the light signal would still cross it faster than the spacecraft. As the destination drew closer, the ship would also need to prepare for deceleration. If it continued moving at extreme speed, it could pass through the entire star system in a short time and leave Proxima Centauri behind. The shorter distance experienced by the passengers would also reduce the time available to react. Every measurement, adjustment, and decision would need to be made before the destination star filled a large portion of the sensor's view. But before stopping became the main concern, the passengers would already be facing another change. The light from Proxima Centauri would no longer reach the spacecraft at the same frequencies measured by telescopes on Earth. Because the vehicle was moving directly toward the source, the incoming light waves would arrive in more rapid succession. The colors on the displays would begin shifting away from their original appearance, while forms of radiation normally invisible to the human eye could be pushed into different energy ranges. Proxima Centauri would be drawing closer in the travelers' measurements, but the light guiding them toward it would also be changing. The faster the spacecraft moved, the farther the colors would shift from anything the human eye had known. The more the directions across the sky would appear distorted, and the more energy the darkness ahead would contain. The nearest star would no longer be merely a destination growing larger on a screen. It would become the brightest feature in a sky transformed by the velocity of the observer. The space ahead of the ship no longer resembles the broad, star-filled sky seen from Earth. Light that once arrived from many directions becomes concentrated into a narrow region around the bow, making stars that were once off to the sides appear to slide forward. Some sources grow brighter, others shift into entirely different colors, and familiar stars may vanish from the range of human vision even though they continue to shine. The sky does not go dark because the stars have disappeared, but because the spacecraft is moving so quickly that their light is no longer received in the same way. At familiar speeds, the colors of the sky barely change with the motion of the observer. An airplane flying toward the sun does not cause daylight to suddenly turn purple, because the aircraft is moving far too slowly compared with the speed of light. Even the fastest spacecraft today travel at only a tiny fraction of that limit, so any shift in the incoming light is far too subtle for the naked eye to notice. But when an interstellar ship reaches a significant fraction of light speed, the waves arriving from ahead begin to be received in more rapid succession. The light in front of the ship delivers more oscillations within the same amount of time. The frequency detected by the sensors rises, and the photons carry more energy. A source that originally emitted red light might appear orange, yellow, or white as the spacecraft accelerates. If the ship continues moving faster, visible light from that source could shift into blue, then violet, before leaving the range of human vision and entering the ultraviolet. The star would still be directly ahead and still releasing energy, but the passengers would no longer be able to see it with unaided eyes. Behind the spacecraft, the opposite process occurs. The ship is moving away from the sources it has left behind, so waves arriving from the rear are received less frequently. Their light is stretched toward longer wavelengths. Blue may gradually shift into red, while red light may leave the visible range and move into the infrared. A star that once shone clearly behind the ship could fade on the observation display, not only because the distance is increasing, but also because the energy of the received light has decreased. The Sun provides the most familiar example. Soon after the spacecraft leaves the solar system, its home star would still be the brightest point behind it. Distance would make the Sun appear smaller over time, but the ship's velocity would also shift its light toward the red. If the vehicle moved fast enough, the light once visible to human eyes could be displaced into the infrared, causing the Sun to disappear as a familiar yellow-white point on an uncorrected display. It would still be shining and sending energy into space, but the energy reaching the ship would now occupy a different region of the spectrum. Meanwhile, infrared sources that were invisible ahead of the ship could be shifted into visible light. Cold clouds of dust, extremely dim stars, or regions emitting thermal radiation that could not be seen from Earth might appear on the sensors in unfamiliar colors. The sky would not simply become bluer in front and redder behind. The layers of radiation normally divided into radio waves, microwaves, infrared, visible light, ultraviolet, and higher energy regions would begin sliding across one another's boundaries in the spacecraft's measurements. For this reason, the outside view could not be understood through ordinary vision alone. A star disappearing from a visible light display would not mean that it had gone dark. Its energy might have shifted into the ultraviolet or even higher frequencies, where specialized sensors could still detect it. A dark region ahead would not necessarily be truly dark either, because it might contain infrared, microwave, or radio radiation being shifted into different energy ranges as it met the spacecraft. The changing frequency of light caused by motion is not limited to an imaginary interstellar voyage. Astronomers have long used this effect to measure the movement of stars, gas, and galaxies. When the characteristic lines in a star's spectrum shift toward the red, it can indicate that the source is moving away from the observer. When they shift toward the blue, the source may be approaching. Through tiny changes in light, humans can measure the velocities of objects so distant that no spacecraft could ever reach them directly. For an interstellar spacecraft, however, the same effect would no longer be subtle. The velocity would be high enough that colors would not merely shift by a small amount within the spectrum, but could transform the entire appearance of the sky. An observation system designed for slow travel would quickly become inadequate. Cameras built for visible light might be overwhelmed by sources ahead or fail to detect objects that had shifted beyond their sensitive range. The sensors would need to cover many wavelengths and continuously adjust to the vehicle's current speed. A wide region of sky that once surrounded the spacecraft could contract into a smaller field of view near the bow. Familiar constellations would become distorted because each star would shift by a different amount across the apparent sky. The patterns humans once connected through imagination from Earth would disappear. Constellations would no longer preserve their old shapes. The spaces between stars would change, and a region that had once been behind a passenger's shoulder might appear close to the direction in which the ship was traveling. If someone could look directly through a perfectly safe window, the sky would not resemble the long streaks of light often shown in science fiction films. Stars would not necessarily become white lines racing across the glass simply because the spacecraft was moving at a steady velocity. Light streaks usually appear when a camera moves during a long exposure or when an image is used to represent the sensation of acceleration. In an instantaneous view, the stars could still appear as points of light, but their positions, colors, and brightness would be dramatically altered. Ahead of the ship, a concentrated region of brightness might appear, where light from many directions had been compressed into a narrow angle. Behind it, the sky would grow darker and redder, while much of the view along the sides would seem drawn forward. Depending on the velocity, the amount of light visible to human eyes might decrease rather than increase. Many stars that originally emitted visible light would be shifted beyond the visible range, leaving the sky looking emptier without instruments capable of translating other wavelengths. This could make the passengers feel as though the universe were narrowing toward the front of the spacecraft. Yet, the surrounding space would not actually be drawn into a single point. The stars would remain in their physical locations, while the concentration would arise from the way the directions of incoming light were measured in such a rapidly moving frame. As the spacecraft slowed down, the sky would gradually open again. The stars would drift toward more familiar positions, and their colors would move closer to those seen by a slower observer. Instead of windows, the spacecraft might rely on cameras and sensors placed behind several layers of protection. Some instruments would face forward, others would observe the sides and rear, while additional sensors would measure different regions of the spectrum. The raw data would not necessarily be shown directly on a screen, because its colors and intensities might lie beyond what the human eye could safely process. Computers would need to reduce the apparent energy, shift the wavelengths, and reconstruct the sky as an image the passengers could understand. An ultraviolet source ahead might be translated into blue on the display. Infrared radiation behind the ship could be reconstructed as red or orange. Regions that were too intense would be dimmed, while weaker sources would be brightened so the passengers could still recognize the structure of the sky. The image shown inside the cabin would therefore no longer be what the human eye would see if someone could stand outside. It would be a computer-generated translation of the real radiation environment surrounding the spacecraft. After COB, WMAP measured the cosmic microwave background at higher resolution, creating a more detailed map of the ancient sky. Regions differing by only tiny fractions of a degree in temperature were rendered as patches of color, helping scientists estimate the age, composition, and geometry of the universe. Later measurements continued to improve, but the basic meaning remained unchanged. Even the places that seem darkest between the stars contain a layer of light from the distant past. Aboard an interstellar spacecraft moving far faster, the difference would no longer be subtle. The microwave background ahead would be compressed, shifted to higher frequencies, and received with greater energy. Behind the ship, it would be stretched, appearing colder and weaker. A layer of radiation that seems almost uniform around Earth would become highly uneven from the passenger's point of view. At more moderate speeds, the radiation ahead would still remain mostly within the microwave range, though with a higher apparent temperature. As the spacecraft moved closer to the speed of light, those photons could be shifted toward shorter wavelengths. Depending on the velocity, some of them might gradually move into the infrared or even higher energy regions. The darkness ahead of the ship would no longer have the same properties as the darkness humans had always known. This does not mean the cosmic microwave background would instantly become a wall of fire that destroyed the spacecraft the moment it reached a high speed. The danger would depend on the exact velocity, the duration of exposure, the design of the shielding, and the way the energy was absorbed. Even so, it reveals an important limit. The spacecraft could not focus only on bright stars or easily recognized sources of radiation. Even the faintest background radiation in the universe would be transformed when the vehicle moved fast enough. Forward-facing cameras would have to deal with far more energy than maps created on Earth would suggest. Sensors could become saturated if they were not designed for the shifted frequency range. Optical materials transparent to visible light might absorb ultraviolet or X-rays strongly, causing them to heat up and fail. An instrument that worked well while the spacecraft was moving slowly could become unusable after the velocity increased. The passengers might choose to view a reconstructed version of the sky that resembled what they had seen before leaving Earth. Computers could partially reverse the color shifts, restore Proxima Centauri to red, return the constellations to more familiar positions, and reduce the brightness of the region ahead. Such an image would help people navigate and preserve a sense of familiarity, but it would not be the actual view being received by the sensors. Another mode could display the sky closer to the raw data. The region ahead would then brighten in colors that no longer corresponded directly to the original spectrum. Stars from the sides would crowd toward the center, and the view behind would grow darker. Some sources would appear and disappear as their wavelengths moved through the sensitivity range of the instruments. The passengers could watch the same star gradually change color during acceleration, even though nothing within the star itself had changed. The transformation of the sky would also affect timekeeping and communication. Radio signals arriving from Earth behind the spacecraft would be stretched as the vehicle moved away from the source. The receiver would detect a lower frequency than the one originally transmitted, so the communication system would need to know the relative velocity in order to locate the signal. Without adjustment, a receiver locked to a fixed frequency band could miss the message entirely, even though the radio waves were still reaching the ship. Signals from ahead would experience the opposite effect. If a transmitter were located near the destination star, its radio waves would be shifted to higher frequencies as the spacecraft approached. Any interstellar communication system would need to operate across a very wide frequency range or continually predict the shift throughout the journey. The same message could reach the ship in a form very different from the one in which it was sent. Even the rhythm of a signal would change in observation. Pulses emitted at regular intervals from a source ahead might arrive closer together, while pulses from behind would become more widely separated. This would not allow the travelers to receive information faster than light, but it would change the rate at which the parts of a signal sequence arrived as the spacecraft approached or receded from the source. These changes could create a profound sense of isolation. Earth would not only grow smaller and disappear behind the ship, but its light would also drift away from familiar colors. The constellations that once helped humans recognize direction would no longer preserve their shapes. The sky, one of the few things the passengers might have expected to remain the same everywhere, would also be transformed by their velocity. As the spacecraft began to slow down, the effects would gradually weaken. The concentrated region of brightness ahead would widen. The stars would drift toward less distorted positions, and the light from Proxima Centauri would move closer to the spectrum measured by an instrument at rest within that star system. The cosmic microwave background would also become more uniform around the ship as its relative velocity decreased. If the vehicle eventually came to rest near the destination star, the sky would once again spread across every direction. The constellations would still not resemble Earth's sky because the passengers had moved to a different location in space, but the concentration caused by extreme velocity would no longer dominate the view. The sun would appear as a distant star behind them, while the stars of the Alpha Centauri system would become prominent sources of light in the new sky. At low velocities, particles of dust are almost harmless. A grain may be far smaller than the width of a human hair and drift through space for millions of years without causing anything remarkable. But as the spacecraft approaches the speed of light, it does not need to encounter a large meteorite for a collision to become dangerous. Even an extremely small particle striking the hull could release energy within a very narrow area, producing heat, plasma, and secondary particles capable of penetrating deeper into the ship. The light ahead could be converted into data. Cameras could be placed behind shielding, and radiation could be filtered before it reached the living quarters. But dust is not an image on a screen. It is real matter lying directly in the spacecraft's path, and the ship cannot make it disappear simply by closing its eyes. NASA once sent a spacecraft called Stardust to collect dust particles far smaller than the width of a human hair. They were light enough to drift through space for long periods and fragile enough that a collision at excessive speed could heat, deform, or shatter them before scientists could bring them back to Earth. To preserve these tiny pieces of matter, Stardust did not use a rigid metal plate or an ordinary container. Instead, it carried a transparent, extremely lightweight material made mostly of empty space. Known as aerogel, this material could slow a dust particle gradually over a short distance rather than forcing it to stop all at once. But for a spacecraft traveling close to the speed of light, particles once considered fragile would no longer behave like dust. They would become projectiles, striking the hull with energy, concentrated into such a small area that the entire journey could be threatened by something the human eye would never see. Stardust was launched near the end of the 20th century, with the primary mission of approaching Comet Wild 2 and collecting particles escaping from the region around it. As the spacecraft passed its target, dust grains struck the aerogel collector fast enough to create tiny tunnels inside the material. Each tunnel was wider at the entrance and gradually narrowed, resembling the trail of an object slowed through many layers of extremely thin gas. The particle eventually came to rest deep within the track, retaining enough of its structure for scientists to remove and study it after the sample capsule returned to Earth. Stardust carried more than a collector for cometary dust. During part of its journey, another side of the collection system faced the surrounding space in search of particles that might have originated beyond the solar system. Distinguishing interstellar dust from material produced within the solar system was far from simple, because the samples were extraordinarily small and many traces could be confused with material from the spacecraft itself. Even so, the mission demonstrated that humans could directly capture particles traveling through space, rather than only infer their existence from the light of distant stars. Before and after Stardust, other spacecraft also detected streams of dust entering the solar system. During its journey beyond the familiar orbital plane of the planets to observe the Sun from different angles, Ulysses detected dust grains whose direction of motion did not match that of most interplanetary dust. The measurements revealed a small stream of material passing through the Sun's region of influence, consistent with the solar system's movement through the surrounding interstellar medium. Cassini also carried a dust analyzer during its journey to Saturn and throughout its years of operation within that planetary system. It measured particles from many different sources, including material around the rings, icy moons, and grains whose trajectories suggested that they were not gravitationally bound to the solar system. These measurements did not turn the space between the stars into a dense region of matter, but they confirmed something important. What humans often call a vacuum is not completely empty. Between the Sun and Proxima Centauri, there is no clean tunnel prepared in advance for a spacecraft. That space contains sparse atoms of hydrogen and helium, ions stripped of their electrons, free electrons, charged particles moving under the influence of magnetic fields, high-energy cosmic rays, and grains of dust made from rock, metal, carbon, or ice. Their density is extremely low compared with the air on Earth. Within a small volume, the ship might pass through almost nothing, but the journey to another star extends across trillions of kilometers. So even a sparse environment can produce countless interactions when accumulated across the entire distance. The moment a dust grain strikes, the forward shield would not resemble a bullet punching a round hole and coming to rest. At extreme velocity, matter would have no time to deform gradually or move aside in the familiar way. The front of the particle and the material it struck would be compressed, heated, and ionized almost instantly. Their original atomic structures would break apart. Electrons would separate from nuclei, and an intensely hot cloud of plasma would form at the point of impact. The dust, grain, and part of the shield could vaporize before the surrounding material had time to carry the heat away. The newly formed plasma would continue expanding and strike deeper layers. Some of the energy would become heat, some would travel through the material as shock waves, and some would produce high-energy photons and secondary particles. Fragments thrown from the shield could continue inward at lower speeds than the original grain, yet still move fast enough to cause further damage. This idea is appealing because a magnetic field would not require a solid sheet of material to cover the entire front of the spacecraft. A system of superconducting magnets could create a region of influence extending beyond the hull, beginning to deflect particles before they reached the surface. If it worked effectively, it could reduce the amount of charged matter directly striking the shield, while also helping protect the passengers from some cosmic rays and high-energy particles arriving from the destination star. However, magnetic fields do not act effectively on every kind of matter. An electrically neutral dust grain could pass through the magnetic region with almost no change in direction. Many dust grains carry a small electric charge because of their interactions with light and plasma in space, but their charge, size, and composition vary widely. A field strong enough to bend every significant dust particle away over a safe distance might require enormous magnets, immense amounts of energy, and an extremely heavy supporting structure. If a dust grain could be ionized before reaching the spacecraft, a magnetic field might deflect the resulting charged fragments. One possible approach would therefore use lasers or radiation beams to heat an object ahead, turn it into plasma, and then use electromagnetic fields to push that plasma aside. But detecting a tiny dust grain at a sufficiently great distance would already be a serious challenge. The spacecraft would be approaching at extreme speed, leaving very little time between detection and impact. A larger object would be easier to detect, but it would also be more dangerous. Radar or LiDAR could scan the region ahead for objects that reflected a strong enough signal. Once a target was identified, a high-power laser could vaporize part of its surface and create thrust that shifted it away from the spacecraft's path. The ship might also make a small course correction to avoid the object if it were detected early enough. At near light speed, however, even a slight change in direction would place enormous demands on the structure and propulsion system. While the required reaction distance might be so great that the sensors would not be sensitive enough to see the target, the laser would not need to destroy the object completely. It would only need to alter its trajectory enough that the particle was no longer directly in the spacecraft's path. But a dust cloud, containing countless tiny grains, could not be handled one particle at a time in this way. Detection systems would be better suited to rare, larger objects, while passive shielding would still have to absorb the smaller and more common material. A multi-layer shield could combine different materials instead of relying on a single solid block. The first layer would be designed to withstand the initial impact and vaporize the dust grain. An empty gap behind it would allow the plasma to expand. The next layer would absorb the dispersed fragments, while deeper layers would be optimized to stop neutrons, high-energy photons, and other secondary particles. Sensors positioned between the layers would monitor the damage, allowing the system to identify which regions needed reinforcement or replacement. On a voyage lasting many years, the shield might not remain a fixed component throughout the entire journey. Fresh panels of material could be moved forward to replace sections that had been worn away. Robots outside the spacecraft could reposition protective blocks, repair damaged areas, or add more material in the direction receiving the heaviest impacts. The entire bow could be designed as a sacrificial structure, gradually surrendering its own material to keep the living quarters behind it safe. But the repair robots would also need protection. Whenever they moved beyond the shield, they would be directly exposed to the high-energy particle environment. Radiation could damage their electronics, dust could erode their moving joints, and their cameras could deteriorate rapidly. External repairs while the spacecraft raced through space at near-light speed might be possible only with automated devices operating from behind the protected region, working for brief periods or using mechanical arms extending outward from the rear. Another idea would be to send a cloud of material ahead of the spacecraft. Instead of waiting for interstellar dust to strike the shield, the ship could release a stream of small particles moving in the same direction. This cloud would create a protective region some distance in front of the bow. Interstellar dust would collide first with the released particles, breaking apart or becoming ionized, while the products of those collisions would have more time to spread out before reaching the hull. If the cloud consisted of extremely small particles, it could cover a wide area with less mass than a solid shield. The spacecraft would continually release more material to maintain the necessary density. The protective region would not need to stop the incoming dust completely. It would only need to break it into smaller fragments, distribute the energy, and allow magnetic fields to deal with the newly charged plasma. But to remain ahead of the spacecraft, those particles would need to reach a velocity equal to or greater than that of the main vehicle. Accelerating additional protective systems would require more energy, and every device lost would need to be replaced from supplies carried aboard. An interstellar vessel might need an entire formation traveling ahead of it, including sensors, laser emitters, plasma generators, and sacrificial shields, rather than a single hull moving alone through the darkness. No solution would remove the risk entirely. Physical shielding could protect against neutral dust, but it would increase the spacecraft's mass. Magnetic fields would not add mass in the same way as a thick wall, but they would require magnets, energy, and cooling systems, while still being unable to deflect every particle. Lasers might handle larger objects if they were detected early enough, but would struggle against countless particles too small to track individually. A cloud of material ahead could disperse impacts, but it would need to be continuously replenished and controlled. A practical design might have to combine all of these methods. The bow would carry a multi-layer shield surrounded by a magnetic field that deflected charged particles. Farther ahead, a stream of material would be released to break apart incoming dust. Sensors and lasers would search for rare, larger objects, while robots monitored the erosion of each protective layer. The living quarters would be placed deep behind the bow and surrounded by water, fuel, or hydrogen-rich materials to reduce secondary radiation. Over time, maps of the forward shield would begin to reveal regions suffering greater erosion. The flight direction could be adjusted very slightly to distribute impacts across different sections rather than allowing one area to absorb the entire flow of matter. The spacecraft might also rotate slowly around its axis, allowing different points on its surface to pass through the forward direction and share the damage more evenly. Interstellar space would not need to contain enormous asteroids to become dangerous. A region with only slightly more dust than expected could force the spacecraft to change its plans. A thin interstellar cloud, almost impossible to see from Earth, could significantly increase the number of impacts over many months. The passengers might still see an almost empty darkness on their displays, while the shield ahead continuously lost material. A longer route through a region with less dust might be safer than the shortest straight path. The spacecraft could avoid known interstellar clouds, regions around highly active stars, or areas containing greater amounts of debris. But every additional section of the journey would increase the required time and energy. Choosing between a short, dangerous route and a longer, safer one would become part of mission planning, much like a ship avoiding storms at sea, except that information about the interstellar environment might already be years out of date by the time the spacecraft arrived. Even without encountering a single large grain of dust, individual gas atoms would continue striking the bow. At near light speed, they would become a directed stream of radiation arriving from ahead. Hydrogen is the simplest and most abundant element in the interstellar medium, but every hydrogen nucleus hitting the shield would carry energy that had to be absorbed. This particle flow could heat the surface, generate secondary radiation, and interfere with the sensors. Inside the living quarters, the passengers might see no direct sign of this environment. The temperature would remain stable, artificial lighting would continue imitating day and night, and the engines would maintain their steady rhythm. Only in the control room would graphs of shield erosion, surface temperature, and radiation flow continue to change. A slowly rising curve might matter more than any dramatic warning, because it would reveal that the spacecraft was gradually losing its ability to protect itself. After many years, the shape of the bow might be different from the day of departure. The outermost shield panels would have been replaced, some of the reserve material would have been consumed, and the magnetic system might need to operate at higher power to compensate for weakened areas. The spacecraft would still be moving toward Proxima Centauri, but every kilometer traveled would have left a mark on its structure. This creates another limit on velocity. Even if the engines had enough energy to accelerate further, the shield might not survive the environment at the higher speed. A small increase in velocity would raise the energy of every impact, causing the rate of erosion to rise. The spacecraft might be forced to travel below the capability of its engines because the protective materials had become the true limit. Research into materials, magnetic fields, plasma, and radiation shielding could gradually reduce the problem. The first interstellar probes would provide real data about erosion in the space between stars. Every impact mark on their shields would reveal which models were accurate, which materials were most durable, and how much the actual environment differed from predictions. Before humans ever boarded such a vessel, many generations of uncrewed spacecraft might have traveled the same route and created a more detailed map of what lay within the darkness. If the shield worked as designed, the magnetic field deflected most charged particles, and the detection systems dealt with larger objects in time, the spacecraft could continue toward Proxima Centauri. Small impacts would still occur, but they would not penetrate the protective layers. The reserve material would gradually decline within acceptable limits. The living quarters would remain pressurized, and the passengers would know about the outside environment only through technical reports. The shielding would have carried the spacecraft safely through gas atoms, charged particles, and interstellar dust. The forward instruments would still be functioning, the living compartment would remain sealed, and the travelers would finally see the destination star system. But now, the greatest danger would no longer be something capable of striking the ship. It would lie within the very velocity the spacecraft had spent years and an enormous amount of energy trying to achieve. To remain there, the vehicle would need to remove most of that motion. To enter orbit, it would have to transform from the fastest object humanity had ever built into a spacecraft, slow enough to be captured by the gravity of the star and its planets. Without a way to do that, all the shielding, engines, and years spent traveling would only bring the passengers close enough to see a new world before they swept past it forever. After years of travel, the destination planet finally appears on the screen as something more distinct than a point of light. A thin atmosphere traces the curve of its horizon. Moving white bands may be clouds, while dark blue and brown regions below suggest oceans or broad continents. The sensors still do not have enough data to confirm whether this world supports life. But for the first time, the travelers can see another place as a true planet, rather than as a few subtle changes in the light of its star. Yet the spacecraft still carries the enormous velocity accumulated throughout the entire journey. Without a way to slow down, only a few hours later, the planet that has just appeared will shrink back into a point of light behind them, while the ship continues into the darkness, never to return. Throughout the acceleration phase, velocity was the journey's greatest objective. Every system was designed to make the spacecraft move faster, from its energy source and engines to its shielding and the passenger's ability to withstand force. While the destination system was still light years away, gaining even a small additional fraction of speed could significantly shorten the journey. But once the destination lies directly ahead, that same velocity becomes the most dangerous obstacle. The ship cannot enter orbit around a planet while still moving at a significant fraction of the speed of light, nor can it simply shut down its engines and wait for the star's gravity to capture it. In space, there is not enough friction for a vehicle to slow naturally as a car does when the driver releases the accelerator. If the engines shut down midway through the journey, the spacecraft will continue moving at nearly the same speed. It may pass through the star system, with the gravity of its celestial bodies bending its path only slightly, then escape from the other side and continue traveling for thousands of years. To stop, the vehicle must change its motion through a force powerful enough and sustained for long enough. The energy used to accelerate does not disappear simply because the travelers can now see their destination. The spacecraft carries that energy within its own motion. To enter orbit or approach a planet safely, most of its velocity must be removed. If the vehicle accelerated with a reaction engine, the most direct method would be to turn the ship around, point the engines forward, and produce thrust opposite its direction of travel. In principle, braking requires an effort comparable to acceleration, because the spacecraft must change its velocity by nearly the same amount it accumulated after leaving Earth. The mass devoted to deceleration may be much greater than it first appears. The braking fuel requires tanks, pipes, control valves, and cooling systems. Those components must survive years of radiation, vibration, and collisions with interstellar dust, then operate precisely when the spacecraft reaches its destination. A small valve failing to open at the proper moment could make the entire braking fuel supply useless. The system therefore needs backups, but every redundant component adds still more mass. On a crewed journey, deceleration also cannot begin too late. The spacecraft cannot wait until the planet fills the screen before turning around and firing its engines. At an acceleration gentle enough for the human body to tolerate, braking may take months or years. The turnaround point must lie far from the destination system, perhaps in a region where the planet is still too distant to be seen clearly by direct sensors. Turning the ship and using its engines to brake is simple in principle, but it works only if the spacecraft carries enough energy for the entire mission. An uncrewed vehicle can be designed in a very different way. Instead of attempting to stop, it may only need to reach the destination system as quickly as possible, collect data during a flyby, and transmit that information to Earth before continuing onward into space. This is the approach taken by some interstellar proposals that come closest to technologies whose individual components are already being studied. Breakthrough Starshot has proposed using an extremely powerful laser array to accelerate gram-scale probes attached to light sails to about 20% of the speed of light. At that velocity, an ultralight device could reach the Alpha Centauri system in a little over 20 years, but the basic architecture is intended mainly for a flyby and would not carry enough fuel to stop. NASA has also funded and examined directed energy propulsion concepts for extremely lightweight probes, in which lasers or remotely transmitted power could accelerate small devices to speeds far beyond those of present spacecraft. Some studies assume gram-scale vehicles reaching relativistic velocities, but the size of the probes and the infrastructure required reveal the enormous gap between an uncrewed instrument and a spacecraft containing living quarters. A vehicle traveling at 20% of the speed of light could cross 1 astronomical unit, roughly the average distance between Earth and the Sun, in less than an hour. If the useful observation region surrounding the planet and star extended only a few astronomical units, the entire close approach phase might end within several hours. After more than 2 decades crossing the darkness, the spacecraft would have only a brief interval in which to complete the most important part of its mission. The cameras would need to be aimed at the target before arrival, because at that speed, rotating the instruments after the planet had passed might already be too late. Sensors would have to capture many images within a short period, analyze the atmosphere's spectrum, measure temperature, and search for clouds, ice, or notable gases. Instruments measuring magnetic fields, plasma, and dust would need to record the environment around the planet, while the computer continually checked the flight direction to determine which data came from the star, the planet, or the space beyond. Such a flyby could still have enormous scientific value. Only a few close-range images might reveal far more detail than telescopes on Earth could observe. Direct measurements of the environment surrounding the planet could confirm the presence of an atmosphere, a magnetic field, or chemical components that remote observations could not distinguish. If many small probes were sent together, each could view the target from a different angle or replace others that failed along the way. But for humans, a flyby is not a destination. After spending years inside a sealed cabin, passengers could not simply watch a planet appear on a screen and accept that it would be behind them forever, only a few hours later. They could not step outside, enter orbit, explore the surface, or take enough time to determine whether the world was truly safe. A crewed spacecraft would need to slow down enough to be captured within the star system. It would first have to enter a stable orbit rather than racing directly between the celestial bodies. Only after slowing could the vehicle spend months or years observing the star, measuring radiation, mapping the planets, and identifying regions containing dangerous dust. The ship would need to find a safe path among several gravitational sources. In a multiple star system such as Alpha Centauri, the motion of stars and planets is more complicated than it would be around a single star. Dust regions, asteroids, and material carried by stellar winds could also create dangerous environments. A decelerating spacecraft would have to update its trajectory continuously, so it did not pass too close to a star, collide with a planet, or get thrown out of the system before stabilizing. If the travelers wanted to land, they would also need a separate vehicle capable of leaving the mothership, passing through an atmosphere, and returning to orbit. If the planet lacked a suitable surface or contained a toxic atmosphere, the spacecraft would need enough resources to continue searching for another destination. Carrying only enough fuel to reach one specific point would turn every error in the original predictions into a threat to survival. A long-term expedition would also need to consider the return journey. If the spacecraft used nearly all its fuel to slow down, it might become stranded in the destination system. That could be acceptable if the mission were designed as a one-way voyage, but if the passengers intended to return, they would need a new energy source or infrastructure capable of refueling the ship. The destination planet could not be assumed to contain refined materials, factories, and suitable equipment simply because it looked similar to Earth from a distance. A light sail offers one possible way to decelerate without carrying all the necessary reaction fuel. As the spacecraft approaches a star, the pressure of its light can act on a large sail. If the sail is angled correctly, radiation from the destination star could produce a force opposite the direction of motion, gradually slowing the vehicle. This force would be extremely small for a heavy spacecraft, but it might become significant for an ultralight probe carrying a sail with a large area compared with its mass. Studies have examined combining light pressure with the gravity of the Alpha Centauri stars to slow an interstellar sail. In these models, the probe might pass close to one star, use its light and gravity to change direction, and then continue toward another. However, the arrival velocity would need to be far lower than 20% of the speed of light if the vehicle were to be captured instead of simply passing through. This would extend the journey from a few decades to many decades or more than a century, while also requiring an extraordinarily light sail and a trajectory of extreme precision. A star's gravity can help change the spacecraft's direction, but it does not automatically remove the ship's energy in every situation. A vehicle passing a solitary star may accelerate as it falls into the gravitational field, then lose nearly the same amount of speed as it climbs away. To use gravity for permanent deceleration, the spacecraft would need to combine it with light pressure, a companion star, an atmosphere, a magnetic field, or some other mechanism capable of transferring energy into the surrounding environment. A magnetic field offers another possibility. A magnetic sail would not require an enormous sheet of solid material. Instead, it would create a wide magnetic region ahead of the spacecraft. As the ship moved through plasma and stellar wind, the field would deflect charged particles. The reaction produced by changing the motion of those particles could gradually slow the spacecraft. Rather than carrying all of its reaction mass from Earth, the vehicle would use the interstellar medium or the wind of the destination star as material for braking. This possibility is appealing because a magnetic sail could begin working from a great distance, where the stellar wind had already begun influencing the surrounding environment. As the spacecraft drew closer, particle density would rise and the braking force could become stronger. However, its effectiveness would depend on the vehicle's mass, the strength of the magnetic field, the plasma density, and the arrival velocity. Studies combining magnetic and electric sails suggest that deceleration could take years or decades, even for vehicles far smaller than a crewed city moving through space. A system capable of generating a powerful magnetic field would require superconducting magnets, cooling equipment, and a stable energy source. The magnetic region would need to be wide enough to interact with a significant amount of plasma, while the coils and supporting structures that created it would still have to remain within the spacecraft's mass limits. If the environment around the star were thinner than predicted, the braking force might be insufficient. If the star's magnetic field varied strongly, the spacecraft's trajectory could also change in ways that were difficult to control. Studies of combined photogravitational and magnetic assistance suggest that magnetic fields might help slow or redirect a sail, but could also produce large deviations if the sail's charge and trajectory were not controlled precisely. A more straightforward approach would be to build a laser system at the destination. If Earth could use a beam of energy to push a sail from behind, then a laser array in the destination system could illuminate the front of the sail and slow the vehicle down. The spacecraft would not need to carry a massive supply of braking fuel because the energy source would already be waiting at the destination. But such a system could not appear on its own. Before humans departed, a fleet of uncrewed spacecraft would have to reach the star system, decelerate by some other method, extract materials, and build the necessary infrastructure. They would need to generate power, assemble optical elements, synchronize thousands or millions of emitters, and direct a laser beam across a great distance toward a sail approaching at extreme velocity. The infrastructure could begin with very small spacecraft. The first devices might only survey the star system, measure the environment, and search for resources. A later generation could carry robots capable of extracting material from asteroids or small moons. Over many decades, they might build energy collectors, communication stations, and automated factories. Only after the entire system was operating reliably would the crewed mission leave Earth. The people who designed the laser array might not live to see the spacecraft launched. The first robots could arrive after technology on Earth had changed completely. The system near Proxima Centauri would need to operate autonomously for many years without rapid assistance, because every repair command sent from Earth would take more than 4 years to arrive. Even if the infrastructure were built successfully, the crewed spacecraft would still need to enter the precise corridor where the braking system could act upon it. A laser beam could not chase a vehicle that had drifted too far off course, while changing direction at relativistic speed would require an enormous amount of energy. Star maps, planetary positions, and the motion of the Alpha Centauri system would have to be predicted accurately many years in advance. Every fuel-free braking method replaces one form of mass with another form of complexity. A light sail reduces the amount of fuel aboard the spacecraft but requires an extremely lightweight material with an immense surface area. A magnetic sail uses the environment outside the ship but needs magnets and a power supply. A destination laser array removes braking fuel from the spacecraft but demands an entire industrial system built in advance at a place no human has ever reached. None of these solutions requires only a more powerful engine. Interstellar deceleration is a problem involving the entire mission architecture, beginning before the day of departure and continuing for years after the spacecraft reaches the destination system. Cruise velocity, vehicle mass, braking method, and the possibility of returning must all be chosen together. If one part changes, the rest of the design must change with it. The spacecraft continues slowing until the gravity of the star system can hold it within a controlled orbit. The engines no longer need to oppose most of its interstellar velocity, but only adjust its path among the celestial bodies. The energy of dust impacts decreases, the sky returns to a less distorted appearance, and the light of the destination star approaches the color that instruments on Earth once predicted. Suppose all of these problems are eventually solved. The spacecraft slows at the right moment, enters a safe orbit, and discovers a planet where humans can step onto the surface. The shielding has survived the interstellar dust, the engines still function, the life support systems have not failed, and the passengers remain healthy enough to explore their destination. If the travelers decide to return, the entire problem begins again in reverse. The spacecraft must be refueled or receive energy from the infrastructure that has been built. It must leave orbit, accelerate through interstellar space, endure another bombardment of dust, then turn around and brake as it approaches the solar system. Aboard the ship, time dilation may allow the travelers to age by only part of a lifetime. They would still experience every year of exploration and the return journey, but far less time might pass for them than for the world they left behind. The ability to stop would allow them to remain in the new world, while a sufficiently powerful engine could bring them back to the place where the journey began. But Earth would not pause while they accelerated, decelerated, and explored another planet. The clocks at home would continue running, cities would continue changing, and generations would continue to be born and grow old. The travelers might solve the greatest challenges of velocity, cross the interstellar dust, and stop precisely at a world more than 4 light-years away. What they could not stop was the time that had passed behind them. The spacecraft leaves the destination system beneath an unfamiliar morning sky, with the faint red light of Proxima Centauri low behind it and the newly explored planet slowly shrinking on the display. After years beneath another sky, the travelers turn the bow toward the sun once more. They know the return journey will repeat nearly all the challenges they faced before. Acceleration, passage through the interstellar medium, protection of the forward shield, the turnaround, and deceleration upon entering the solar system. But this time, it is no longer dust or radiation that leaves them silent. Earth lies ahead, and no one knows how closely the world waiting there will resemble the one preserved in their memories. Inside the cabin, life continues according to its familiar rhythm. Artificial lights come on in the morning. Plants are tended, the air is filtered, and the ship's systems continue producing their steady vibration. The travelers still sleep a normal number of hours, still feel tired after a long shift, and still notice more gray in their hair when they look in the mirror. Time dilation does not freeze them, erase aging, or turn a year aboard the ship into a few minutes. Every day they live is real. Earth is simply accumulating more time along its own path. The first signals from home still carry familiar voices. A mother sits before a camera in the old room and explains that the tree outside the window has grown, a new station has opened in the neighborhood, and the house still keeps an empty chair just as it did on the day of departure. She speaks more slowly now. Her hair has turned gray, and she sometimes pauses to search for a word. When the recording ends, the traveler understands that the image left Earth years earlier. While the signal crossed the darkness, the woman continued living, and she may no longer exist by the time her greeting reaches the ship. The distance between stars turns every conversation into a letter that cannot be answered in time. A question sent home may take years to arrive, and the response requires several more years to return. The travelers might ask about an operation when the patient has only just entered the hospital. But the answer arrives long after everything has ended. A birthday message may reach someone after they have already grown another year older, while an apology may appear on the screen only after the person who needed to hear it has become a memory. Gradually, the children once lifted toward the camera to wave begin recording their own messages. They talk about school, work, and changes in the city. A few transmissions later, they appear with partners and then with children who did not yet exist when the spacecraft left Earth. The travelers still remember their young faces, but the people on the screen are now adults carrying the voices and gestures of another generation. There is no single moment announcing that childhood has ended. The transformation passes quietly through one video after another. Then strangers begin to appear. They introduce themselves as the grandchildren or great-grandchildren of those who once stood at the launch site. They know every crew member's name, know the old house, know the stories passed through the family, and know the departure date from history books. But they share no memories with the travelers. They have never sat at the same table, heard the same footsteps in the hallway, or watched the same rain fall on Earth. To them, the traveler is a living member of family history. To the person inside the spacecraft, they are strangers carrying a few familiar features in their faces. As the ship moves closer to the sun, newer signals from Earth begin catching up with it one after another. During the outward journey, the spacecraft was moving away from the waves transmitted from home, increasing the intervals between received messages. On the return journey, it is racing directly towards signals that have been traveling through space for years. Earth's history may therefore appear more rapidly on the screen, not because time on the planet has suddenly accelerated, but because the spacecraft is encountering successive layers of light belonging to different moments. A city appears with new towers. Only a short time later, according to the ship's clocks, another transmission reveals that the entire district has been rebuilt. Familiar streets disappear beneath new transportation networks, coastlines are reshaped, and places that were once suburbs become crowded urban centers. Elsewhere, former cities may have been returned to forests, water, or protected land. Earth does not need to suffer a single catastrophe to become unfamiliar. The planet only needs to keep living, rebuilding, and changing through many generations. The names of countries may no longer match the old maps. Some regions have united, others have separated, new alliances have formed, and borders once considered permanent survive only in historical records. Language has changed as well. At first, there are only a few unfamiliar words and slight differences in pronunciation. Later, the computers must add subtitles, explain concepts that did not exist when the spacecraft departed, and translate entire sentences whose sounds the travelers still recognize but can no longer fully understand. Their own voices have become ancient. Recordings from the spacecraft are used in schools and museums as examples of language from an earlier period. The way they refer to machines, countries, and professions is studied as living historical evidence. When the travelers send a new message, many people on Earth must listen through translation systems, even though both sides still speak languages descended from the same original tongue. The travelers never stopped speaking their native language, but that language continued changing without them. The mission itself gradually becomes an event in history books. The launch is restored in high-resolution images, the sound of the engines is reconstructed, and the old launch site becomes a memorial. Children learn the names of those aboard the spacecraft, as they once learned about explorers from centuries earlier. Decisions made during a few tense minutes are analyzed across generations. Certain remarks are removed from their original context and turned into slogans, while inaccurate stories are repeated for so long that they nearly become accepted as truth. In one family transmission, a young woman places a box on the table containing old letters and a key passed down through several generations. The key once opened the house where one member of the expedition grew up, but that house was demolished long ago. The street was renamed, the neighborhood was rebuilt, and no one knows exactly where the old doorway once stood. An ordinary object has become evidence that a place once existed. As the spacecraft enters the outer solar system, the sun grows from a point of light and the planets begin appearing on the sensors. But surrounding them are structures absent from the old maps. Orbital stations, communication networks, settlements, and unfamiliar transportation routes. The spacecraft that was once the most advanced machine in civilization is now received as an artifact from another age. Engineers on Earth must relearn its old protocols, while the ship's computers require layers of translation software to understand modern signals. The communication delay falls from years to months, then to days and hours. For the first time in a very long while, the travelers can ask a question and know that the person on the other side will still be living under nearly the same circumstances when the answer returns. A reception coordinator appears on the screen, greets each crew member using speech reconstructed from their era, and explains the route home. She knows a great deal about them, but has never met anyone from their families. The conversation is almost happening in real time, yet the sense of distance remains. Earth appears as a blue and white sphere that seems almost unchanged. The ocean still reflects sunlight. Clouds still curl around the continents. And darkness still moves across the surface, with the planet's familiar rotation. From a distance, the travelers might believe they are about to return to the same place they left. Only when the cameras move closer does the new world reveal itself. Cities glowing in different shapes, coastlines that have shifted, and structures offshore reflecting light where there was once only open water. The spacecraft enters orbit, and the passengers are eventually brought down to the surface. Real wind touches their skin after years of hearing only air moving through pipes. The gravity of an entire planet pulls their bodies downward, heavier than the sensation created by the engines. The sea is still there. Clouds still drift overhead, and when night falls, the moon still crosses the sky with its familiar dark regions. Nature has changed slowly enough for memory to recognize it, but the house is gone. The old neighborhood has become a park, a new residential district, or part of a much larger city. Modern maps must overlay historical data onto the landscape to show the approximate location of the street that once existed. There is no door to open, no room to enter, and no chair remaining from those first messages sent across the stars. An archival center may reconstruct the house from photographs, videos, and old scans. The traveler sees the hallway, sunlight across the floor, and faces restored from recorded data. The voices can be heard again, but every sentence was spoken long ago. Technology may predict how someone would once have responded, but a prediction is not the person themselves. The simulation may be painfully convincing, yet it cannot create a new shared memory with the one who has returned. Time dilation carried the traveler into Earth's future more quickly according to their own age, but it did not create a path back into the past. When the engines reversed direction, the years that had passed at home did not begin running backward. If someone left at the age of 30 and returned at only 40 while Earth had lived through many generations, then they truly had entered the future with a body only 10 years older. But no choice could return them to the morning when their family was still standing at the launch site. The greatest cost of near-light speed travel may therefore lie not in fuel, radiation, or the grains of dust that once vaporized against the shield. Those physical obstacles, however difficult, are still engineering problems. A sufficiently advanced civilization may discover stronger materials, more efficient engines, and more durable protection systems, but no equivalent shield can protect an era. The person who returns can still continue living. They may meet the descendants of their family, learn a new form of the language, and help build better spacecraft. They do not necessarily have to spend the rest of their life alone, because human beings can still form new relationships. But a sense of belonging cannot be replaced entirely by admiration. They need people who understand a story without requiring an explanation. Remember the same song, and know why a certain street corner once mattered. Those people now exist only in recorded data. If traveling faster causes home to recede farther into time, then a more powerful engine does not completely solve the desire to journey far away and still return. It allows the passengers to cross immense distances within less personal time, but at the same moment, it widens the separation between them and the world they left behind. Perhaps the final path is not to keep pushing the spacecraft faster, but to find a way to shorten the distance itself, so the journey would no longer need to pass through years that Earth could never wait for. A spacecraft with mass cannot continue accelerating until it passes through the speed of light. Each time the engines add more energy, the ship moves only a little closer to that boundary, while the final step remains forever out of reach. But what if the spacecraft did not need to cross all the space between two stars directly? What if the region ahead could be shortened, the region behind stretched, or two places separated by many light years connected through a shorter path built into the structure of space-time itself? The problem would no longer be how to make the spacecraft move faster than light. It would become a question of whether space itself could be altered in a way that allowed the ship to arrive without crossing every kilometer between its departure point and destination. This idea is not entirely unfamiliar to modern physics. The universe has already shown that distances between regions of space can change. Very distant galaxies are moving away from us, not only because they are traveling through a stationary background, but because the space between galaxies is itself expanding. A photon crossing that space has its wavelength stretched throughout the journey, causing light from distant. Across sufficiently large distances, the rate at which the separation between two regions of the universe increases can exceed the speed of light. This may sound like a violation of the limit that has governed the entire journey, but the two situations are not the same. No galaxy near us is directly racing past a beam of light beside it. What is increasing is the amount of space between two very distant locations. A spacecraft moving through its local region of space would still be unable to catch a beam of light emitted ahead of it. Light would continue to preserve its limiting speed in every local measurement. The expansion of the universe simply shows that distance is not an unmoving stage across which objects travel. The stage itself can change over time. In the early universe, space may have passed through a period of extraordinarily rapid expansion. Regions that were once very close together were separated by immense distances within an extremely short time. The matter within them did not need to race through space faster than light, as a spacecraft might attempt to overtake a photon. The distance between those regions increased instead. This fact opens an intriguing possibility in the imagination. If nature has already caused space to change, could a sufficiently advanced civilization create a small, controlled distortion of its own? Perhaps the spacecraft would not need to move faster than light if the space ahead contracted while the space behind expanded. The destination would draw closer without the passengers ever reaching a local velocity beyond the cosmic limit. This is the foundation of the idea commonly known as a warp drive. In this model, the spacecraft remains inside a region of relatively undisturbed space. The area ahead is contracted, while the region behind is expanded. The ship does not race through the surrounding space faster than light. Instead, the entire region of space containing it is carried forward like a bubble sliding across the structure of the universe. Creating a region where space contracts in front and expands behind would require an extremely unusual distribution of energy. Some early versions of the model demanded areas of negative energy density, something that does not exist as a conventional fuel that could be mined, stored in a tank, and fed into an engine. Quantum physics does include limited situations in which the energy within a small region is described as being lower than the surrounding vacuum level. The Casimir effect is often mentioned in these discussions, where two conducting surfaces placed extremely close together alter the state of the quantum fields between them. But measuring a tiny quantum effect does not mean humans can collect an enormous quantity of negative energy and use it to bend space around a spacecraft. Even if a warp configuration can be written with lower energy requirements than the earliest models, the fundamental questions remain. Humans do not know how to create that geometry, what form of matter could sustain it, or whether any device has ever produced a warp bubble in nature or in a laboratory. A conventional engine generates thrust from the spacecraft itself. A pilot can increase power, reduce it, or change direction based on sensor data. With a warp bubble, the motion depends on the shape of spacetime outside the cabin. If the passengers cannot control the entire region from within, external infrastructure may need to create the path in advance. A warp drive might therefore be less like a vehicle free to travel anywhere, and more like a route built through space beforehand, with systems at the departure point and destination generating the distortion and guiding the spacecraft through it. but placing equipment at the destination would require humans to reach that location by some other method before the first warp route could ever operate. Stopping the bubble also raises questions with no known answers. During ordinary near-light speed travel, the spacecraft must remove its kinetic energy by turning around and braking. With warp travel, the ship may not carry an extreme local velocity, but the distorted region of space still contains energy and structure that must somehow return to a normal state. What happens to that energy when the bubble collapses? Is it released as gravitational waves, radiation, or some other disturbance? Could the spacecraft stop gently at its destination? Or would the collapse of the warp region create an event powerful enough to destroy the very place it intended to reach? An engine designed to avoid the danger of interstellar dust might accidentally concentrate that same dust and light into a greater hazard at the end of the journey. No experiment has shown how real matter would behave around a warp bubble, because no such bubble has ever existed for scientists to measure. A deeper problem involves the order of cause and effect. If a spacecraft could reach a distant location before a light signal emitted at the same moment, observers in other states of motion might describe the order of events in ways that produce contradictions. In some situations, the ability to transmit information effectively faster than light could create a path for a signal to return to a time before it was sent. Someone might then receive a warning about an event before deciding to send that warning. If they changed their actions because of the information, the original reason for sending the message might never occur. Loops like this are not merely confusing storytelling devices. They touch the foundations of physics, where causes must precede their effects in every observable process. The speed of light, therefore, does more than limit how far humans can travel. It helps preserve a consistent order of events. Any vehicle that attempts to bypass that limit would have to show that it does not create a path for information to travel into the past, or face the possibility that nature contains some mechanism that prevents a warp bubble from forming. So far, no one knows the answer. A more complete theory of quantum gravity may reveal that warp structures are forbidden. It might instead allow a highly restricted version that cannot be used to create paradoxes. Every present conclusion still rests on models that have never been tested with a real device. If warp travel attempts to move an entire region of space, another idea seeks to connect two distant points through a shorter passage. Rather than gradually contracting the distance ahead throughout the journey, a wormhole would create a direct tunnel between two locations in space-time. Humans have never observed a traversable wormhole. Extremely compact objects such as black holes can curve space-time strongly, but a black hole is not automatically the entrance to a safe tunnel. When matter crosses the event horizon of an ordinary black hole, there is no known path that allows it to emerge at some other distant location. Some mathematical solutions describe bridges between separate regions of spacetime, but many of these structures close too quickly or contain regions through which matter cannot pass and emerge again. Keeping a wormhole open generally requires an unusual form of matter or energy distribution, creating a problem similar to the one faced by warp drive models. Even if microscopic wormholes existed at the quantum scale, enlarging one enough for a spacecraft would be an entirely different challenge. The tunnel would need to be wide enough that the ship did not touch regions where gravity changed too sharply. It would also have to remain stable long enough for the entire vehicle to pass through without collapsing midway. Tidal forces inside a wormhole could pull different parts of the spacecraft with different strengths. If the curvature changed too rapidly, the bow and stern would experience unequal forces, stretching or crushing the structure. A tunnel might be mathematically possible and still remain completely unsuitable for humans or any fragile instrument to cross. Radiation could also accumulate within such a structure. Light entering a wormhole might shift in energy, reflect, or circulate along complex paths. If photons became concentrated, the region around the entrance could grow hot or contain dangerous levels of radiation. No real wormhole exists for sensors to test these predictions. A natural wormhole may already connect two distant regions, but no telescope has confirmed the existence of such a structure. Unusual gravitational effects in the sky have many more familiar explanations, including black holes, neutron stars, dark matter, and the distribution of galaxies. An object cannot be called a wormhole simply because it bends light or produces a signal that is difficult to understand. Even if a candidate were found, humans would need to observe it for a long time to determine whether it was stable. An uncrewed probe would have to be sent first, but if the entrance lay far from Earth, reaching it would itself become an ordinary interstellar journey. The idea could solve the problem of distance only after humanity had already crossed a vast distance to find and examine it. Wormholes are also directly connected to the problem of time. If the two entrances experienced different motions or gravitational conditions, clocks at either end could fall out of synchronization. The tunnel might then connect not only two locations, but two different moments. This would return us to loops of cause and effect, for which no clear solution exists. Quantum effects might destabilize a wormhole as soon as it was about to become a time machine. Nature might not allow such a structure to remain open for long, but this is still speculation, because no one has ever had a wormhole to test. In recent years, wormholes have sometimes been discussed alongside quantum entanglement. Two particles that once interacted can remain part of a shared state, in which the results of measurements reveal strong correlations even after the particles have been separated by a great distance. When one particle is measured, the result is connected to the result obtained from the other, in a way that cannot be explained by assuming that each particle simply carried a predetermined set of ordinary properties from the beginning. This once led quantum entanglement to be described as an instantaneous influence across distance. It is therefore easy to imagine that humans may have discovered a way to send messages faster than light. If two particles located near different stars remain connected, could someone manipulate one of them to transmit a word, an image, or a warning instantly to the other side? The correlation appears only when the two sides compare their data. To make that comparison, they must still exchange information through an ordinary method, such as radio waves or light. That comparison signal cannot travel faster than light, so quantum entanglement cannot become an instantaneous telephone between Earth and Proxima Centauri. Quantum teleportation is often misunderstood in a similar way. In experiments, the quantum state of a particle can be reconstructed at another location through entanglement and an ordinary communication channel. The original particle of matter does not travel across the distance instantaneously, and the information required to complete the process must still move at no more than the speed of light. Quantum entanglement remains one of the most profound phenomena in physics. It is being studied for quantum computing, secure communication networks, and measurements of extraordinary sensitivity. But according to current understanding, it does not provide a way to send messages faster than light, nor would it allow passengers to communicate instantly with home. The three ideas most often mentioned when humans search for a path around the light speed limit therefore remain far removed from real technology. Warp travel depends on altering the geometry around a spacecraft, but no suitable matter, energy source, or control method is known. Wormholes would create shortcuts through space-time, but none have been observed, and there is no known way to keep one open for matter to pass through. Quantum entanglement creates correlations across distance, but it does not allow anyone to choose the outcome and use it to transmit information instantly. Spacecraft, such as Stardust, have captured dust in aerogel. Ulysses and Cassini detected particles passing through the solar system from the interstellar environment, confirming that the space between stars is not completely empty. The path to the stars did not begin with an enormous engine shaking the structure of space. It began with discrepancies lasting only tiny fractions of a second on clocks, with grains of dust trapped inside an almost transparent material, and with protons completing more than 10,000 circuits per second through a tunnel buried deep beneath the ground. Each individual piece of evidence may seem very small. A proton is not a spacecraft. A clock drifting by a few billionths of a second is not a journey across entire ages. A grain of dust inside aerogel is not an interstellar storm. An experimental sail cannot yet carry humans to Proxima Centauri. The speed of light is not merely a number that makes the stars seem distant. It prevents signals from arriving before they are sent, preserves the order in which causes precede effects, and keeps the past from becoming a place that humans can easily revisit and alter. Perhaps one day, a new theory will reveal a way to control space-time that we cannot yet imagine. Wormholes may exist only within equations that can never become physical structures. Warp drives may always require conditions that nature does not allow, or an entirely different path may already be hidden within data that humanity is not yet sensitive enough to recognize. But on a small planet orbiting the sun, humans continue measuring every photon, every grain of dust, and every tiny deviation in time. We cannot yet bend space at will, open a wormhole, or create a warp bubble. Even so, each measurement is making the boundary between what is impossible and what is merely not yet possible a little clearer. Humanity will follow traces left long ago: protons racing through CERN's tunnels, atomic clocks carried across the sky, grains of dust resting inside aerogel, and light from the nearest star that crossed more than 4 years of darkness before reaching human eyes. The stars are separated from us by more than empty space. Between us and them lie energy, matter, radiation, time, and the limits that keep the entire universe operating in a consistent order. To leave Earth and travel far enough to touch another sun, humanity must learn more than how to cross a distance. We must learn how to live within the structure of space-time itself.